Hello everyone, welcome to PW. So till now we have already completed about the basics of the sequential circuit. But again, I'm interested to tell you something very interesting in the entire sequential circuit, and that is what we call finite state machine. Okay, so you are going to love digital electronics after studying this finite state machine. So very important and very interesting. So uh, in general, whenever we talk about a finite state machine, we will always move like what is a finite state machine, how to design a Mealy and Moore model. But I will go in a different pattern. First, I will let you know about Mealy and Moore model through one question. What is the state, how to draw the state diagram, how to write the state table. And later on, I will move again back to the Mealy and Moore model, how to construct any sequence in case of sequence detector. Okay. Now, please see today's goal. We will talk about a revision of the previous session a little bit. So in the last class, I have tell you about how to construct a synchronous sequential circuits. In that, we have also observed about the resistor type counters like resistor type counters like Johnson counter or a ring counter. Okay, and we also learn about the error name as a creeping error in case of a Johnson counter. We can also call it as a lockout error. Sometimes we call it as a lockout error in a Johnson ring counter. Now, I am going to discuss about the, today I am going to discuss about the finite state machine. Later on, we will move towards the Mealy and Moore circuit. Okay, state reduction sequence detector. Can I proceed? Okay. So all of the revision part already we have done. Now I am going to discuss about the finite state machine. Let us suppose if the output is depending upon the previous state, then in general, one can think that there will be a infinite possibilities of the input state. So we need a resistor having infinite capacity to store, but it is not physically possible. So whatever sequential circuit we design is always a finite only. Okay. Now please observe. It is a summarized model which describes a synchronous sequential machine. Okay. It is a summarized model which describes the synchronous sequential circuits. Further observe. In sequential circuit, output depends upon the present input as well as past history. Hence, it is needs to infinite capacity of storing them. We need infinite capacity for storing them, which is practically not possible. Yes, sir. Since it is not possible to implement a machine with an infinite storage capacity, so finite state machines are used. So whatever you will hear about the synchronous sequential circuit, all will have a finite state zone. Okay. Next, see, finite state machine are sequential circuits whose past history can affect their future behavior in a finite number of ways only. In a finite number of ways only. Is it okay? Like if I am going to design some circuit, then it should be behaves exactly same after some clock pulses. If I am going to design such a circuit which is not going to retrieve its state again, then that type of circuit is said to be infinite machine. Okay. So finite state machines are sequential circuit whose past history can affect their future behavior in a finite number of ways only. In a finite number of ways only. Is it okay? Yes, sir. So this is just a basics about the FSM, finite state machine. In short, we called it as SFM. Now please observe block diagram of a finite state machine. Okay. I'm trying to show you a better block diagram. Please observe here. In a finite state machine, state machines can be of two type. Okay. It can be a Mealy or a Moore type. All the clocked synchronous sequential circuits are divided as a Mealy and Moore. If you observe here, I have tried to show you the representation of the clock. Okay, this will be the previous state. Okay, so previous state depending upon that, and present input. This is your present input. So previous state and present input depends on depending on that, your next state is going to be changed. Again, that state is going to be stored somewhere. Is it okay? So this is just a basics about the synchronous sequential circuits. Okay, all the things are synchronized with the clock. Now please observe here. The clocked synchronous sequential circuits are generally divided into two categories. First one is called as a Mealy model circuit, and the second one is called as the Moore model circuit. Both Mealy and Moore are itself sufficient to construct any desired finite state. So sir, why we are using sometimes Mealy and sometimes Moore? There is some advantages and some disadvantages. Okay, like first I am going to compare about the Mealy and Moore circuits. Now please observe here. First I am going to show you the block diagram of the Mealy model. Please write down. Clocked synchronous sequential circuits are of two types. Clocked synchronous sequential circuits are of two types: Mealy model circuit and Moore model circuit. Mealy model circuit and Moore model circuit. Now first, I am interested to discuss about the Mealy model circuit. Please see. The output of Mealy machine or model is a function of present input and present state. Very important. It means if my output is Z, then Z is the function of Qn as well as present input, some X, Y, Z or something. Okay. Yes, sir. So please observe here. I am trying to show here the input. This is your input. Is it okay? It goes to the next state detector. Then we will have next state Qn plus 1. That is again going to be stored in a memory, as well as some of the next state and input, some of the next state and input goes to the output of detector, and output of detector is the function. Z is the function. Z is the function of X and Qn both. So this is the basic difference between the Mealy and Moore. Mealy model, output is the function of present input X. If you observe, these are X. Okay. Yes, sir. Output is the function of X and present state Qn. So in Mealy model, output is the function of present input and present state. Output is the function of present input and present state. I have represented here Z is equals to the function of X and Qn. Is it okay? Yes, sir. Now please observe. You need not to draw it. Just you need to remember that your Mealy model circuit output function is the function of output is the function of both present input and present state. Okay. Now please observe here. Next, I am interested to talk about Mealy also, Moore also. What is Moore model? In Moore model, the difference is that in Moore model, output is the function of present state Qn only. It is not the function of present input X. It is not the function of present input X. This is your input. It is not the function of input. It is the function of present state only. So you can say output Z is the function of present state only. So this is the basic difference between Mealy and Moore model. Just by observing the circuit, you can directly identify whether the given circuit is a Mealy circuit or a Moore circuit. If you are observing that output is the function of input as well as present state, then it's a Mealy. And if the output is the function of present state only, then it's a Moore. Is it okay? Great, sir. Up to this part, I am hoping everything is clear. Come to the next differences between the Mealy model and Moore model. Now, it's an important one. Please see. Most of the time in different ESC exam or a PSU exam, they will ask some of the points related to this. Please see. Moore model, the output of machine is the function of present state only. Output of the machine is the function of present state only. Output of the machine is the function of present input as well as present state. So this is the difference between Mealy and Moore. Is it okay? Now next observe, in Moore model, change in input doesn't affect the output. Change in input doesn't affect the output. However, in case of Mealy model, since output is the function of present state as well as present input, so change in input may affect the output of the circuit. Is it okay? Great, sir. Next, in Moore machine, number of states required to implement any function is more than comparative to Mealy machine. So it requires more number of states for implementing same function. When number of states are increasing, it means number of flip-flops are increasing, delay is increasing. Is it okay? When we talk about Mealy, then it requires less number of states for implementing the same function as the function implemented by the Moore machine. Is it okay? Last one, Moore machine, it is easy to design. So because it is easy to design, it is taking more cost. Okay. And if we talk about Mealy, it is complex to design, harder to design comparative to the Moore model. So you can say, sir, its cost is lower, number of flip-flops needed will be less as the number of states are less. So these are the basic differences between the Moore and Mealy machine. Now I am interested to understand about the Mealy and Moore model. So I am explaining it with the help of one example first. Okay. Now please see. First of all, you need to identify whether the given circuit is a Mealy circuit or a Moore circuit. Whether the given circuit is a Mealy circuit or a Moore circuit. Maybe this is wrong, so don't just go through this. Just you need to identify whether the given circuit is a Mealy circuit or a Moore circuit. Sir, for that I need to understand the output. Whether output Z is the function of present states only, or output Z is the function of present state as well as present input. So when I saw this is X bar, X is the input. Yes, sir. So when I saw this is the X bar and this one is your X. It means it is representing your output function Z. Output function Z is the function of both, Q1, Q2. So these are the present state. So output Z is the function of present state as well as present input X. That indicates the given model is a Mealy model. Is it okay? Great, sir. So sometimes just you need to identify whether the given model is a Mealy or Moore. So now you know how to identify the Mealy or Moore model. Is it okay? Now please observe. Consider the Mealy model sequential circuit shown below. Derive the state table and state diagram. Derive the state table and state diagram. So now I am going to show you how to write the state table and what is actually a state diagram. Okay. Please observe, in this I have tried to represent two flip-flops, flip-flop A and flip-flop B. In flip-flop A we have D1 Q1 Q1 complement and flip-flop B D2 Q2 Q2 complement. You know about the flip-flop. Both the flip-flops are connected with the same clock pulse. Both the flip-flops are connected with the same clock pulse. It means it's a synchronous sequential circuit. Yes, sir. We know that, sir. D flip-flop, whenever input appears to D flip-flop, the same input will be on its latch, that is Q1 or Q2, after applying the clock pulse. Yes, sir. We know about the truth table of the D flip-flop. Same we will get in the latch of the D flip-flop as we are going to apply onto the input of D flip-flop. Yes, sir. Now please observe. I'm interested to find the input to D. So what is input to D? Now please observe here. What is input to D? This is X bar. Yes, sir, X bar. And if you observe this line is coming from, please observe here. If you observe this line, so this line is coming from here. That is Q2 complement. Can I say this? Yes, sir, it's a Q2 complement. It's a Q2 complement. So, sir, you can write X bar Q2 complement. Is it okay? Great. Now, if you observe here, what are the inputs? We need to identify the inputs first. Very important. If you observe here, what is the input? input to this AND gate is, one input to this AND gate is this Q1 complement. Is it okay? Yes, sir. So one input is Q1 complement. Q1 complement. Okay. Another input is, another input is, another input is, another input is this one. This input is Q2, sir. Q1 complement Q2. Q1 complement Q. Is it okay? Yes, sir. So we have the expression at D1. What is the expression at D1, sir? The expression at D1 is, the expression at D1 is x1 complement Q2 complement plus of Q1 complement Q2. Can I write in this way? Yes, sir. Great. Now please observe here, Q1 complement Q2. Q1 complement Q2. Is it okay? Yes, sir. Now come to the next one. Sir, this one is Q1 complement. So same is available here. So x Q1 complement. It means what is at D2? At D2 we are getting D2 to be equals to x Q1 complement plus of Q1 complement Q2. Is it okay? Yes, sir. So we can easily analyze about the inputs to the flip-flop A and B. Always before applying the clock pulse, we need to identify the inputs to the flip-flop. Then apply the clock pulse and follow the truth table. The same is going to be applied to anything, any sequential circuit. Okay, sir. Now please observe what about Z. What about Z, sir? Sir, Z will be equals to x Q1. Yes, sir. And what about this one? Q1 complement Q2 complement. So x complement Q1 plus of x Q1 complement Q2 complement. So in that way we can analyze the inputs to the different flip-flop. Is it okay? So in that way we can easily find out the outputs. I'm just going to show you. Please observe. Individually you can find it out like expression of A. So since I have represented that flashing line that is not possible to show in the PDF, so I have represented in this way also, so that you know how the wires, how the leads are connected to the input. Okay. Yes, sir. Great. Now please observe what is Q2 bar, what is D1. D1 is equals to, we have observed x bar Q2 bar. Let me write it here. We have observed x bar Q2 bar. I'm just writing here again. Please see. X bar Q2 bar plus of Q2 Q1 complement. Can I write in this way? Yes, sir. Already I have identified the input applied to D flip-flop. I'm just observing each of the flip-flop individually now. Okay. Yes, sir. Similarly, you can write for flip-flop B also. Okay. Similarly, we can write for flip-flop B also. This is for flip-flop A. I'm just representing the excitation and output expression. Okay. So I'm interested here just to know about the excitation to D1. So excitation to D1 is x bar Q2 bar plus of Q2 Q1 complement. Similarly, if you observe flip-flop B, then flip-flop B, please observe for flip-flop B, this will be your x Q2 bar. Yes, sir. And Q1 complement Q2. So you can write it as x Q2 complement plus of Q1 Q2 complement. Can I write in this way? One is your x Q2 complement Q1 Q2 complement. Another one is your x complement Q2 complement Q2 Q1 complement. Is it okay? X. Okay. There will be a little bit mistake I have done. That is your x Q1 complement. It is not x Q2 complement. So in flip-flop B, this is x Q1 complement. So my typist made a mistake here while writing Q2. Please make it as Q. Okay. Yes, made a mistake. So please correct it. This is your Q1, this is your Q. Okay, up to this part everything is clear, sir. Please let me correct it. This is your X Q1 complement plus of Q1 Q2 Q1 complement. Q2 Q1 complement. Yes, sir. Great, sir. We have for flip-flop A X Q2 complement Q1 Q2 complement. X Q2 complement Q1 complement Q2. X Q1 Q1 complement Q2. Up to this part, I am hoping everything is clear. Q1 complement Q2, I have represented the same thing. Same thing. Q1 complement Q2. Just I am representing Q2 before Q1. Okay. And we have output function Z. So output function Z is Q1 complement Q2, Q2 complement, Q2 complement, Q1 complement, X bar Q1. Okay. And other one is X Q1 Q2. Okay. X bar Q1. So X bar Q1 is okay. Another one is X bar Q1 complement. Another one is X Q1 Q2. So output Z is X complement Q1 plus of X Q1 complement Q2 complement. So X is missing here. X Q2 complement Q1 complement. Kindly correct it. Kindly note it. So now we have Z. I'm writing Z there only. Just remove. I'm hoping up to this part everything is clear. Is it okay? Clear? Great. So I just tried to find the expressions, output expression, input excite, input to D1 flip-flop, input to D2 flip-flop. If we have more number of flip-flops, then in order to analyze the circuit, we will do in the same fashion. Okay, we will do in the same fashion. You need not to draw these again and again. It is just to show you. You can just draw, you can just analyze here only. Is it okay? Up to this part everything is clear. Now we have D1 expression of D2 as well as we have expression of Z. Is it okay? Now we know about the D flip-flop. You need to remember about the truth table of D flip-flop. In a truth table of D flip-flop, what is the next state? Qn plus 1 is equals to D only. In a D flip-flop, whatever will be the present input, same we will get onto the next state. Yes, sir. Excitation table. Excitation table is the table between present state. Yes, sir. Next state with x is equals to 0 or x is equals to 1. Because we have only one input. In case if we have more than one input, then we will see like all the possibilities. Let us suppose if we have xy input, then xy 0 0, next state with xy 0 0, next state with xy 0 1, next state with xy 1 0, next state with xy 1 1. Is it okay? Presently I have identified only one input, that is x. Is it okay? Yes, sir. In the circuit we have identified only one input, that is x. Is it okay? So with the one input, how many possibility? Two possibilities, sir. So I am interested to know about the next state with all of the possibilities. So next state, we have a present state. Present state is in terms of Q2, Q1. Q2 is the output. Q2 is the output of flip-flop B and Q1 is the output of flip-flop 1. Okay? Yes, sir. Its next state, I am writing Q2 plus 1, Q1 plus 1 with x is equals to 0 or with x is equals to 1. Is it okay? And then output is also the function of present state Q2, Q1 as well as present input x. So x will have two possibilities. So I am going to check the output with these two possibilities. X is equals to 0 and x is equals to 1. Is it okay? Yes, sir. How many possibilities of the present state? Sir, 4 possibility. Either both are low, any one of them is high, or both are high. So there are total 4 possibility. There are total 4 possibility. So we have a present state Q2, Q1. I'm interested to know about the next state Q2 plus 1 and Q1 plus 1. It means this is the next state of flip-flop B and this is the next state of flip-flop A. Is it okay? With x is equals to 0 and with x is equals to 1. And then output with x is equals to 0, x is equals to 1. We have total 4 possibility. Either both are low, any one of them is high. Both are high. Now I'm going to check each of the possibilities. Now please observe. First, Q2 plus 1. Q2 plus 1 means onto the flip-flop B. Onto the flip-flop B. I am interested to check the states with x is equals to 0. In case if x is equals to 0, this will become 0. 0 plus Q2 Q1, you will get Q2 Q1 complement. It means your next state Q2 will be high only when Q2 is 1 and Q1 is 0. Is it okay? Under all other condition, what happened? Sir, under all other condition, if Q2 is 0, then you will get a 0 as a next state, because D flip-flop is a transparent latch. Whatever the input on application of clock, you will get same onto the latch. So, sir, Q2 Q1 complement is your D2 now. With x is equals to 0. With x is equals to 0. Q2 Q1 complement is your D2 now. Q2 Q1 complement is your D2 now. Now, please observe this one. What about Q2 Q1 complement? Sir, in this one, Q2 Q1 complement. Q2 complement Q1 complement will become 0. Q2 Q1 complement only at this particular condition it will be high. If you check on any other condition, what we will get? 0 only, sir. The next state of D flip-flop will be 0 only, sir, with x is equals to 0. Now I am going to check with x is equals to 1. We have x is equals to 0. Now I am going to check again this Q2 plus 1 with x is equals to 1. Okay. What happened with x is equals to 1, sir? Please observe what happened with x is equals to 1. If I am going to choose with x is equals to 1, you need not to write, you have to understand this. Very important. Please observe with x is equals to 1. With x is equals to 1, how to identify? If x is equals to 1, we will get here Q1 complement. Q1 complement Q2 plus 1. Is it okay? Yes, sir. I am going to take Q1 complement as a common. So what we will getting? We are getting D2 as Q1 complement. So whatever will be the value of Q1, we will get after applying the clock pulse, we will get Q1 complement over the Q2. Is it okay? Yes, sir. So with x is equals to 1, with x is equals to 1, if the present state is 0, 0. With x is equals to 1, if the present state is 0, 0. What is Q1? 0. Its complement is onto the D1. Is it okay? Its complement is onto the D2. Yes, sir. So what happened to this? Sir, it will become 1. Yes, sir. Q1 complement. Q1 complement is going to be over the Q2 plus 1 on application of clock. Is it okay? Then again for this, sir, 0. For this, sir, 1. For this, sir, 0. How I have represented this? How I have represented this? Sir, next state of B flip-flop when x is equals to 1. Now come to the next state of A flip-flop with x is equals to 0. So I am going to check next state of A flip-flop with x is equals to 0. What happened with x is equals to 0? When we take x is equals to 0, x bar will become, when x is equals to 0, x bar will become 1. This will be Q2 complement. Yes, sir. Now Q2 complement, and this will be your Q2 complement plus of Q2 into Q1 complement. Is it okay? So by using distribution theorem, you can write it as Q2 complement plus of Q1 complement. Can I write in this way? Yes, sir. Because Q2 complement Q2 will become 1, and you can write Q2 complement plus Q1 complement as D1. With x is equals to 0. With x is equals to 0. Yes, sir. It can be clearly observed. With x is equals to 0. So with x is equals to 0, with x is equals to 0, with x is equals to 0. Either you can, if you want, you can represent the minimized one. If you don't want to represent the minimized one, you don't need to represent the minimized one. You can directly go. Doesn't matter. Because Q2 complement means whenever Q2 is low, D1 is high. It means Q1 is going to be high. Is it okay? Yes, sir. On application of clock. Great, sir. So whenever Q2 is low, Q1 is going to be high. with x is equals to 0. So with x is equals to 0, when Q2 is low, Q1 is going to be high. With x is equals to 0, if Q2 is low, Q1 is going to be high. Yes, sir. And also we have observed it will be high when Q2 into Q1 complement. It means when Q2 is high, Q1 is low. Then also your next state is going to be high. Yes, sir. So it means Q2 Q1 complement. Q2 Q1 complement is sir, Q2 is 1 and Q1 complement. If Q1 is 0, its complement is 1, then also you are getting high only. Now come to the last 1 1. In case of 1 1, Q2 is 1, yes sir, and Q1 is 1, so its complement is low, yes sir. Okay sir, so Q2 is 1, so its complement is low, yes sir, and Q2 is 1, but Q1 is 1, so its complement is 0. It means 0 is applying over D1. On application of clock pulse, what we will get? We will get 0 only, sir. So sir, we will get 0 only for Q2 Q1 1 1. We will get 0. This is how you can represent, this is how you can fill this table. Hoping you are able to understand. Can you tell me about x is equals to 1? With x is equals to 1, present state is a 0 0. I am interested to know about the next state of flip-flop A with x is equals to 1. So next state of flip-flop A with x is equals to 1. This is your flip-flop A. Yes sir, with x is equals to 1. With x is equals to 1, its complement will become 0, sir. Its complement will become 0, sir. So when its complement is 0, we are getting 0 here. Yes, sir. Then input to D is Q2 Q1 complement. So it means D1 is going to be high only under the condition of 1 0. On all other condition, D1 will remain low. So next state will remain low. Is it okay? Yes, sir. Great. So from here you can say, sir, Q2 Q1 complement only this will be high. In all other condition it will remain. Now come to the output. Output with x is equals to 0 and x is equals to 1. Very important class. Is it okay? Even if 1 second you miss, then just 0 1 0 1 will be here. So very important. You need to be patient as well as you need to keep your attention over this. Okay. Now last one, with x is equals to 0 or x is equals to 1. What happened with x is equals to 0? Output z with x is equals to 0. Output z with x is equals to 0. With x is equals to 0, this will become 0. Yes sir, so this part will become 0. With x is equals to 0, x bar will become 1. Yes sir, so output z will be equals to q1. So output z will be equals to q1 with x is equals to 0. Output z will be q1 with q1 complement. Okay, q1 complement, sorry, q1 complement. Output z will be q1 complement. Output z will be q1 complement with x is equals to 0. Output z will be q1 complement with x is equals to 0. Is it okay? Output z is equals to q1 complement with x is equals to 0. q1 complement with x is equals to 0. So this is your q1. Its complement is, sir, 1 0 1 0. Is it okay? Great, sir. Now let's talk about output z with x is equals to 1. Output z with x is equals to 1. Output z with x is equals to 1. With x is equals to 1. When we talk about x is equals to 1, then this will become q2 bar q1 bar into x. This will be high. This will be q2 bar q1. This will become q2 q1. Yes sir, plus of. When x is equals to high, then what happens to x bar? This will become low. When this will be low, it means this will be 0. So q2 bar q1 bar. It means z is high only when both q2 and q1 are low. Only when both q1 and q2 and q1 are low. Is it okay? Yes sir. So I am representing here. Sir, z is high only when both q2 and q1 are low. This is how we need to fill the excitation. Are you able to understand? Yes, sir. Now we know how to design how to construct a excitation table. Although this excitation table does not help us directly to draw the state table. Now we have to define some states. Please observe, up to this part everything is clear. I have just used this Q2 Q1 as a present value, and based on the present value we have found the next value with x is equals to 0 and x is equals to 1 onto the circuit. Is it okay? Great, sir. Next I am going to the modified state table. Modified state table. In modified state table, what we do, whatever the value of Q2 and Q1 is given, that value that we have assumed, I am going to name it as a state. Maybe state A, state B, state C, and so on. So I am going to write a modified state table. This is again called as a modified state table. So modified state table. Is it okay? Yes, sir. Again I am writing present state. Present state. Please observe, we have Q2 and Q. Q2, Q1, how many possibilities? 0, 0, 0, 1, 1, 0, and 1, 1. There are total 4 possibilities. Yes, sir. So out of these 4 possibilities, each possibilities I am going to assign a state. Like 0, 0 I am assigning as a state A, 1, 0 as a state B, 1, 1, 0 as a state C, and 1, 1 as a state D. So I am assigning these different conditions of Q2 and Q1 as a state. So now we have a 4 different states: state A, state B, state C, and state D. Okay. Now please observe, we have a present state Q2, Q1 as A, B, C, D. Okay. Now I am interested to know about the next state. Next state means Q2 plus 1, Q1 plus 1. And also I am interested Q2 plus 1, Q1 plus 1. Is it okay? Yes, sir. With x is equals to 0 as well as x is equals to 1. With x is equals to 0 as well as x is equals to 1. With x is equals to 0 as well as x is equals to 1. Okay. This is your Q2 plus 1, Q1 plus 1, Q2 plus 1, Q1 plus 1. Okay. Yes, sir. So now please observe here. If the present state is A, 0, 0. If the present state is A, 0, 0. If the present state is A, 0, 0. Then with the present input x is equals to 0, what is the next state? 0, 1. And what we called a next state? We called a next state 0, 1 as, we called a next state 0, 1 as B. So if the present state is A, then when input x is equals to 0, next state is B, sir. If the present state is A, then with x is equals to 1, if the present state is A, then input x is equals to 1. Next state is 1, 0. What is the next state 1, 0? Next state 1, 0 is basically, sir, 1, 0 is your state C, sir. So with x is equals to 1, if the present state is A, then when input x is equals to 1, next state will become C, sir. Is it okay? Great. Again observe. Present state is B. Present state is B. If the present state is B. Now please observe. If the present state is B. If the present state is B. With the input x is equals to 0. Next state is 0, 1. 0, 1 is a state B only, sir. 0, 1 is a state B only, sir. So 0, 1 is a state B only. If the present state is B. With the input x is equals to 0. Next state is 0, 1 only, sir. So 0, 1 only, sir. It means state B, sir. We can write here as a state B. Yes, sir. Now if the present state is B with x is equals to 1. If the present state is B with x is equals to 1. If the present state is B with x is equals to 1. Present state is B, x is equals to 1. Present state is B, x is equals to 1. Next state is 0, 0. What is 0, 0? 0, 0 is your state A. So 0, 0 is your state A. You can write A here. Are you able to understand this? If the present state is C, C state is 1, 0. If the present state is C, then with input x is equals to 0, next state is. If the present state is C, then input x is equals to 0, next state is 1, 1, sir. Next state is 1, 1, sir. 1, 1 state is defined as a state D. 1 state is defined as state D. Great, sir. Again observe. If the present state is D, if the present state is C with input X is equals to 1, next state is 1 1. 1 1 means, sir, 1 1 means D. 1 1 means state D. Great, sir. What about the output, sir? I am going to write it again. Please see. With the present input 1 1, with the present state 1 1, it means state D. With the present state D, with the present state D, input X is equals to 0. What is next state? Sir, A. Present input 1 1 with X is equals to 1. What is next state? A, sir. So we are getting state A only. Great, sir. So we are getting state A only. Up to this part everything is clear? Yes, sir. Great. Come to the output Z. With the present state 0 and present input X is equals to 0. Present state 0, present input X is equals to 0. Present state 0, present state 0. It means A. X is equals to 0. Next state B and output 1. Next state B and output 1. Great, sir. Next state B and output 1. Hoping you are able to understand this. Great, sir. Again observe. Present state A. Present state A. Present state A. With input X is equals to, with input X is equals to 1. Next state C. Output 1. Next state C, output 1. Great, sir. So with input X is equals to 1, next state C, output 1. With X is equals to 1. If the present state is A, with input X is equals to 1, next state is C, output 1. Great, sir. Again, if the present state is B, 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 please observe here. Present state is B with X is equals to 0. Next state is, sir, B. Output 0, sir. Output 0, sir. Great. Output 0, sir. So we have present state B, next state B, output 0, sir. Again observe. Present state B with X is equals to 1. Next state A, output 0. Next state A, output 0, sir. Great. With the present state C, present state C, X is equals to 0. Next state D, output 1. Next state D, output 1. Next state D, X is equals to 0 and X is equals to 0, output 1. Present state C with X is equals to 1. Present state C with X is equals to 1. Next state D, output 0. Next state D, output 0. Hoping you are able to understand this. How to write? Yes, sir. Present state D, present state D with X is equals to 0. Present state D with X is equals to 0. Next state A, output 0. Next state A, output 0 with X is equals to 0. With X is equals to 1. With X is equals to 1. If the present state is D, with X is equals to 1. Next state A, output 0. Sir, next state A, output 0. Hoping up to this part everything is clear. How to write the modified state table. Now come to the final state table. Okay. Again, I am going to write the modified table. So I am interested to write the next state in terms of ABCD along with its output. Okay, yes, sir. So again I am going to modify this. Please observe. Please observe. Present state A. Present state A. Next state with X is equals to 0. Next state with X is equals to 1. Next state with X is equals to 0. And next state with X is equals to 1. We have to represent like next state comma output. So I am interested to represent in this manner. I am interested to represent it in this manner. Okay. Present state A. Present state A. Present state A. Okay, sir. Present state A. With X is equals to 0. Please observe again. Present state A with X is equals to 0. Next state B, output 1. So I am representing B, output 1. Is it okay? Great, sir. Present state A. Present state A. X is equals to 1. X is equals to 1. Next state C, output 1. So sir, C comma 1. Great sir. Present state B. Present state B. Okay sir. For a present state B with x is equals to 0. Present state B. Present state B with x is equals to 0. Next state is B, output 0. So B comma 0. Yes sir. So we can write B comma 0. Present state B. Present state B with x is equals to 1. Next state D, output 0. So with x is equals to 1, next state D, output 0. Next state D, output 0. Next state D, output. Is it okay? Hoping you are able to understand how to write these things. Yes sir. Just going with a step by step so that you can easily, comfortably understand how we need to draw the state diagram. Present state D, present state C. Now I am interested present state C with x is equals to 0. Next state D, output 1. So D comma 1. Is it okay? Yes sir. So this will become D comma 1. D comma 1. Present state C. Present state C. Present state C with x is equals to 1. Next state D, output 0. So D comma 0. Yes sir. D comma 0. Present state D. Present state D. Present state D with x is equals to 0. Next state A, output 0. Next state A, output 0. So sir, A 0. Present state D. Again I am writing present state D with x is equals to 1. Next state A, output 0. So next state A, output 0. A comma 0. Is it okay? Yes sir. A. This is how we need to write the state diagram finally. Now we have the final modified state table. Next is to draw the state diagram. So how to draw the state diagram? Please observe. We have total 4 states. We have state A, we have state B, okay, state C and state D. So let me represent you in this way, state C and state D. So we have total 4 different state. Okay. Yes sir. If the present state is A, that we have assumed as a 0 0. If the present state is A, if the present state is A, then with the input x is equals to 0, with the input x is equals to 0, this is representing present state. Okay. Yes sir. With the input x is equals to 0, what happened? With the input x is equals to 0, what happened? It goes to next state. Yes sir. Present input A with input x is equals to 0, it goes to next state B. Next state B. And what is the output? Sir, 1. So if you observe, this is representing your present state. Present state. Is it okay? Yes sir. This is representing present input. Present input. Is it okay? And this is representing output. This arrow indicates going towards the next state. Arrow indicates going towards the next state in a Mealy model. Okay. Great sir. Now present state A with x is equals to 1. Next state. Present state A, x is equals to 1. Next state C, and what is the output? 1. Is it okay? Great sir. So first one is input, second one is output, and arrow indicates going towards the next state. Again, present state B. Present state B with x is equals to 0. Next state, the remain B only. And what is the output? Output is 0 sir. Present state B, x is equals to 1. With x is equals to 1, what is the next state? D sir. Output 0. Present state D, present state C with x is equals to 0. Next state D, output 1. Sir, 0, 1. Great sir. Again observe, present state C with x is equals to 1. Next state D, output 0. So you can represent two different things in the same line. From C, it either 0 or 1, whatever will be the input, it goes to the next state only. However, the outputs are different in depending upon the input, whether input is 0 or 1. Now present state is D with input x is equals to 0. Next state A, output, next state A, output 0. With x is equals to 1, next state A, output 0. So this is how we need to construct a state diagram. Is it okay? Great, sir. Sir, you have shown us a circuit. From the circuit, we have constructed a present state and a next state with the input, all possibilities of the input. Then we came to the state table. From this state table, you have represented a state diagram. But if I am interested to design a finite state machine, then how would I design? Whenever user first come to you, he asks about the states first. Like, I want 5 different states. If for input this, the condition goes to this state, else it goes through some other state. In that way, first of all, you need to understand the user concern, and accordingly you will draw the state diagram first. From the state diagram, you will draw this state table. You can construct this state table. Is it okay? Now you have constructed from this to state diagram. So can you construct from state diagram to state table? Yes, sir. If you have a state table, then you can construct a modified state table or excitation table. For the sequential circuit, given below, derive the state table and state diagram. Now, sequential circuit is given. You need to derive the state table and state diagram. Please observe here. How you know about the type of this model, whether it is a Mealy model or a Moore model? Sir, we need to find the output y, whether output y is the function of present state only or present state and present input both. So if you observe, this is your A is the input to this, yes sir, as well as this B, QB is the input to this flip-flop, this output Z. So output Z is function of just QA and QB, it is not the function of X. So it means it is the function of Qn only, it means present state only. That indicates the given model is a Moore model. This is your Moore model. Is it okay? Yes sir, great. So the given model is a Moore model. Great sir. Hoping up to this part everything is clear? Great sir. Now please observe, the given model is a Moore model. For the sequential circuit below, derive the state table and state diagram. So for that I am going to see each of the flip-flop individually, because before applying the clock pulse, we need to identify the inputs to the flip-flop. So I'm just going to analyze the input to the flip-flop. What is the input to the flip-flop? Input to JA. Input to JA is QB, sir. Input to JA is QB, sir. And what is the input to KA? Input to KA is X bar QB, sir. This is your clock. Is it okay? Yes, sir. What is input to JB? JB is X bar, sir, and input to KB is X XOR A. X XOR A. So now we know about the input to JA, KA, JB, KB. Now we know about the input to JA, KA, JB, KB. Is it okay? Great, sir. Next is, if you want, you can analyze each of the flip-flop individually also. So I'm going to show you the each of the flip-flop individually. So we have here we have, this is the clock. Yes, sir. We have JA is equals to B. JA is equals to B, that is QB basically. Yes, sir. And KA is equals to X bar QB. Already we have observed here. X bar QB and QB. Is it okay? Yes, sir. So this is your flip-flop A. Now we know about the inputs to the flip-flop A. Also, I am constructing a JK flip-flop. Next state, it means truth table of the JK flip-flop. So if we know about JA and KA, we can easily identify the next state of the flip-flop. So 0 0 0 1 1 0 1 1. Yes, sir. We know about the truth table of the JK flip-flop. Yes, sir. Great. Similarly, I'm going to analyze this flip-flop A also. We have two flip-flop A and B. Okay, this one is your B flip. We have A and B, two flip-flops. Okay. Now I am interested to understand the input to the B flip-flop. Now what is the input to the B flip-flop? Please observe here. Please observe here. This is clock. This is your clock. Okay. Yes, sir. Now please observe here. Sir, we are getting X bar at JB. So JB is equals to X bar. JB is equals to X bar. Yes, sir. JB is equals to X bar. And KB is equals to, A XOR X. A XOR X. We know about the JK flip-flop, sir. We know about the JK flip-flop. Yes. The truth table of JK flip-flop is truth table of JK flip-flop. Yes, sir. We remember about the truth table of JK flip-flop. We have J, K, Q, N plus 1, 0, 0, 0, 1, 1, 0, 1, 1. So for 0, 0, what you will get? Qn 0, 1, Qn complement. Is it okay? Great, sir. Now please observe. I am interested to identify the inputs to JA and JAKA and JBKB and JBKB. Okay. Yes, sir. Also we have output. What is the output expression? Output expression is, sir, output expression Y is, sir, A XOR B. Yes, sir. Output expression Y is A XOR B. So we have output expression Y as A XOR B. Is it okay? It's a Moore machine because the output is the function of Qn only. So I'm analyzing each of them in the different stages. Okay. See how to construct the state table in case of a Moore machine. Again, first of all, I am defining the states as A and B in terms of 0, 0. How many possibility with the present state? 0, 0, 0, 1, 1, 0 and 1, 1. 4 possibilities, sir. Now, the next state, I am interested to get the next state with x is equals to 0 and x is equals to 1. So, with x is equals to 0, next state A plus 1. So, that is representing next state. Is it okay? Yes, sir. Next state of flip-flop A, next state of flip-flop B. With x is equals to 1. Sir, next state of flip-flop A, next state of flip-flop B. You can also represent in terms of QA, QB. If you want, you can also represent in terms of QA, QB. Instead of writing AB, you may represent in terms of QA, QB. Okay? Yes, sir. Please observe, please observe. We have two flip-flop and the outputs are in terms of QA, QB. QA, QB. Okay? So you can represent in terms of QA, QB also. So let me represent in terms of QA, QB. This will be your QA, QB, QA plus 1, QB plus 1. With x is equals to 0, QA plus 1, QB plus 1. With x is equals to 1, QA plus 1, QB plus 1. It means next state of B flip-flop and next state of A flip-flop with x is equals to 0 and x is equals to 1. Now please observe the present state is a 0, 0. So with the 0, 0, please observe, and the present input x is equals to 0. So I am taking consideration x is equals to 0 first. What happened if x is equals to 0 in flip-flop A? If x is equals to 0, you will get this to be 1. It means here we are getting QB and also here we are getting QB. Is it okay? Yes, sir. So JAKA is equals to QB. In first case, when 0, 0, when QA, QB is 0, 0. In first case, when QA, QB is 0, 0. In first case, when QA, QB is 0, 0. QB is 0. So if QB is 0, input applied to JA and KA is, sir, QB 0, 0. For JK flip-flop 0, 0, next state is remain in the same state, that is called as a hold state. So after applying the clock pulse, you will get the same state as the previous state of QA. You will get the same state as the previous state of QA. Is it okay? Again, with QB is equals to 0, with QB 0, X is equals to 0 and QB is equals to 0. X is equals to 0 and QB is equals to 0. X is equals to, if QB is equals to 0 and X is equals to 0. What happens to QA plus 1? Sir, if QB is 0, it means 0, 0 is applied over the flip-flop A. 0, 0 is applied over the flip-flop A. 0, 0 is applied over the flip-flop A. With X is equals to 0, it means 0, 0 is applied to the flip-flop A. Now, when the clock pulse is applied, it will remain in the hold state. It means QA plus 1 will remain same as before. So, QA plus 1 will remain same as before. It means QA plus 1 will remain same as before 1. Is it okay? Yes, sir. Now, come to the QB 0, QB 1. In case if QB is 1, in case if QB is 1, this flip-flop JA and KA will become 1, 1. If J and KA both are 1, 1, the flip-flop goes into toggle mode, sir. For a toggle mode, what happened? Soon as the clock appear, whatever will be the previous state of QA, it toggles. Great, sir. So, sir, with QB is equals to 1, it goes into toggle mode. So, with QB is equals to 1, with QB is equals to 1, it goes in toggle mode. Toggle mode means, sir, if QA is 1, it toggles to, if QA is 0, it toggles to 1. If QA is 1, it toggles to 0. This is how we can fill the table. Is it okay? Great, sir. Similarly, we can write it for QB plus 1. With X is equals to 0, QB plus 1. With X is equals to 0, QB plus 1. What happens to QB plus 1? With X is equals to 0, it's 0 complement, that is 1. So, JB is going to be 1 only. With X is equals to 0, this will become, sir, this will become a buffer, because if one input of XOR gate is fixed as 0, it will act as a buffer. So, we have A only, that is QA only. It means, sir, whatever will be the QA, same will be appeared onto KB. JK flip-flop, whatever will be K, whatever will be QA, same appeared to KB. JB is equals to 1. So, JB is equals to 1. Now, please observe here. JB is equals to 1. Whatever will be the value of QA, same appeared to KB. So, for 1, 0, next state is 1. Yes, sir. JB is equals to 1 and QA is equals to 0. So, for 1, 0, you will get set state, sir, in case of a JK flip-flop. For 1, QA 1 and JB and KB both 1, 1, it goes into toggle mode, sir. Toggle mode, sir, means if previous state is 0, it toggles to 1. And if QA is 1, it means JB is 1. Yes, sir. Hoping you are able to understand here. JB is equals to 1 with X is equals to 0. Yes, sir. And what is the value of QA? QA is equals to 1. So, 1, 1 means flip-flop goes into toggle mode. 1, 1 means flip-flop goes into toggle mode. Toggle mode means whatever the value of QB previously, it toggles. So, if previous value of QB is 1, it toggles to 0. Is it okay? This is how you can easily fill this table. Similarly, for X is equals to 1. Next, I am going to the X is equals to 1. With X is equals to 1. Okay. For X is equals to 1. Please, we need to understand again with X is equals to 1. For X is equals to 1. X is equals to 1. This will become 0. X bar will become 0. Yes, sir. For X is equals to 1. X bar will become 0. When X bar is a 0. When X bar is a 0. What is appearing here? Sir, 0 only. Yes. And what is appearing here? QB. So, JA is QB, KA is 0. 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 So for 0, it goes into hold mode. So hold mode means whatever will be the value of QA, same appear to QA plus 1. For 0, QB 0, it goes into hold mode. Hold mode means whatever will be the value of QA, same will remain for QA plus 1. Now if QB is 1, KB is 0, QB is 1, then it will become QB is 1. This is 0, set, always 0. This is 1. 1, 0 is a set state. 1, 0 is a set state. So 1, 0 is a set state. It means if QB is 1, then it goes into set state. Is it okay? Similarly, you can write for QB plus 1. Now please observe how to write for QB plus 1. If x is equals to 1, then this will become 1 complement is 0. Yes, sir. If x is equals to 1, then 1 complement will become 0. So JB is 0 and KB is QA. JB is 0, KB is QA. So 0 and QA. Please observe here. JB is 0. Only we have to observe QA because KB is QA. For 0, 0, it goes into the hold mode. Yes, sir. For QA 0, it goes into the hold mode, sir. For 1, for QA 1, sir, JB is 0. For 0, 1, it goes into the reset mode, sir. Yes, sir. For QA 1, JB is 0, sir. QA 1, it goes into the reset mode, sir. Is it okay? Great, sir. Come to the output Y. What happens to output Y? This is your QA XOR QB. What is your output Y? Sir, QA XOR QB. Is it okay? I have represented in terms of QA and QB. So, QA XOR QB, where QA is A and QB is B. So, there is no issue. Okay. Okay, sir. So, QA XOR QB. Now, we need to identify QA XOR QB. If you observe this one, 0, 0, you will get 0. Because XOR gate output is logic 1 only when the two inputs are different. Only when the two inputs are different. Yes, sir. This is how we need to write the state table. Next is state diagram. Very easy. Now please observe how to draw the state diagram. So how many states we have? We have total 4 states. I am going to give the name to these states. Let 0, 0 be the state A. Instead of A, I am writing it as a small a, b, c, d. Okay, because A is two times, so maybe you will confuse. A, B. Okay, this is your state C, and this is your state D. Okay, yes, sir. So you can represent it. You can represent it in a state format like A, B, C, D. Moreover, you may write it here as these states as A as 0, 0, B as 0, 1, C as 1, 0, and D as 1, 1. Okay, so these are your present state. Output is the function of present state only. So for 0, 0, what is your output? Sir, for 0, 0, we are getting, for 0, 0, we are getting 0. For 0, 0, we are getting 0. For 0, 1, we are getting 1. For 1, 0, we are getting 1. For 1, 1, we are getting 0. So there are 4 states. That is the present state oblique output. This is your present state. So this is your present state, and this is your output. Hoping up to this part everything is clear. Great. Now we have to represent the input. If the present state is A, then with x is equals to 0, what is your next state? 0, 1. 0, 1 is your state B. What is your next state? 0, 1. 0, 1 is your state B. If the present state is A, then with input x is equals to, with input x is equals to 0. With input x is equals to 0. With input x is equals to 0. We go to the next state 0, 1, output 1. Present state A 0, 0. with input x is equals to 1, next state A only and output 0, next state A only and output 0, x is equals to 1. Great, sir. Present state B with x is equals to 0, next state D, sir. Present state B, sir, with x is equals to 0, with x is equals to 0, next state is D, sir, output 0 0. Present state B, sir, with x is equals to 1, next state C, sir, next state C, sir. So next state C, sir, x is equals to 1. Is it okay? Great, sir. With x is equals to 0, it goes to D. With x is equals to 1, it goes to C. Present state C, 1 0. With x is equals to 0, it goes to next state D. Okay. So with x is equals to 0, it goes to next state D. Present state D, sir, with x is equals to present state C, sir, with x is equals to 1, with x is equals to 1, next state is 1 0. 1 0 is a state C only, sir. 1 0 is a state C only, sir. X is present state D. Present state D with x is equals to 0. Next state 0 0, sir. 0 0 is a state A. With x is equals to 0, we are moving again back to the state A. Okay. And with x is equals to 1, we are getting 1 0. What is 1 0, sir? State C. So we are getting 1 0 with x is equals to. Is it okay? Yes, sir. This is how we can draw the state diagram of the Moore machine. So now you know about the state diagram of the Mealy and state diagram of the Moore. Arrow indicates going to the next state. There is an input. This is your input. This is your present input. Is it okay? Present state and output. Is it okay? So this is how we can draw the state diagram of the Moore machine. Now I'm hoping you have a clear-cut information about the Mealy and Moore machine. I'm interested to design any desired circuit by using Mealy or Moore. Mostly this finite state machine finds a wide application in digital data transmission. For that, a specific sequence of the output is being detected at the receiving end. So you can easily decode your message in a specific sequence and you can send it, and onto the receiving end that sequence is again retrieved. It means your message is again decoded. So mostly used for the digital data transmission in the format of sequence detector. But before going to the sequence detector, let us talk about the state reduction. What is the state reduction, sir? Very important. Suppose a user asks you to design a finite state machine, and you are just understanding the requirement of user. User say like presently if something is on state A may be a condition, and on giving some input it goes to condition B, then it goes to condition C, then it goes to condition D, and so on. At different conditions, if the present state in the different condition, and by giving the input we may want some different conditions, then accordingly we can construct a state table. Is it okay? Sometimes when we construct a state table, then for every set of possible inputs we are getting exact same next state with the same output. Such a same state and same output we need not to represent in our state diagram, because those are the false state. Is it okay? So for that we can make a state reduction. So by doing the state reduction, number of flip-flops required will be lower, and when you are reducing the number of flip-flop, it means circuit will become simple as well as your circuit cost is decreasing. Is it okay? Great. So now next I am interested to know about the state reduction. Please let me know if you have any issue with anything. Please observe here, state reduction. What is a state reduction, sir? Basically, to avoid the introduction of redundant states. Basically, it avoids the introduction of redundant state. The redundant state or you can say the reduction of redundant state reduces number of flip-flops required and logic gates required, and hence it reduces the overall cost of the final circuit. Is it okay? Great, sir. Further observe, two states are said to be redundant. Two states are said to be redundant if every possible set of input generates the same output. Every set of input generates the same output exactly and the same next state. So if from one state, let us suppose you are in state A, and for every possible set of input you are getting onto the same next state with the same output, then the same next state and same output can be represented by one time only. We need not to represent it many times. Okay? Yes, sir. If two states are equivalent, then one of them can be removed without altering input-output relation. Without altering input-output relationship. Great, sir. Now please observe here. Suppose I am interested to reduce. I am interested to do the reduction of some state. Suppose if we have a state table. Suppose if we have a state table. So we have a state table. Okay, we have a state table. Suppose we have a state table. We have a state table, state A, state B, state C. Please observe here. State A, state B, state C, state D. I think something. Let me correct it. Okay. First this will come, then we need to draw the state table. Please observe. Find the reduced state diagram. We have a state diagram here. Find the reduced state diagram for the state diagram shown in the figure. So this is your present state diagram. Please observe. This is your state diagram. Yes, sir. How many number of different state you are able to see? Like state A, B, C, D, E. I can easily identify there are total 5 states. Okay, sir. So now please observe here. There are total 5 states, sir. There are total 5 states, sir. So I am going to construct a state table now. There are total 5 states, sir. Yes, sir. There are total 5 states. So I am representing present state. Present state are A, B, C, D, E. So we have total 5 different states. Okay. Yes, sir. Now please observe onto the state diagram. Onto the state diagram, this acts as a present input. Yes, sir. Now you will able to understand this. Yes, sir. This will be your output, sir. This will be your output, sir. Arrow indicates going towards the next state, sir. And this will be the present state, sir. So in all the circles, the states are present states, sir. Yes. So we have total only one input. So with the one input, there are two possibilities, 0 or 1. Let the input be X. Let the input be X. So we have two possibility, X is equals to 0 or X is equals to 1. Is it okay? Yes, sir. And output is also given. So I am representing the output part also. Their output is also represented. So output is also dependent upon the input and previous state. So that I am going to represent in terms of X is equals to 0 and X is equals to 1 again. Output Y with X is equals to 0 and X is output Y with X is 0, X is it okay? Yes, sir. Now please observe here. Now please observe here. If the present state is A, if the present state is A, if the present state is A with X is equals to 0, what is the next state? Present state A, x is equals to 0. Next state is B, output 0. Next state is B, output 0. Great, sir. Present state A, x is equals to 1. Next state C, output 0. Next state C, output 0. Present state B, x is equals to 0. X is equals to 0. It is not given, huh? Okay, I got that. Please wait. We can proceed with the same one. Please see. This will be your present. This will be your present input. This will be your output. Arrow indicates going to the next state. And this is your present state. Okay. Present state. Okay, one missing is 0, 1. This is missing here. 0/1. So you can just put it here. 0/1. Rest all things are same. Okay. Now please observe. So already I have mentioned here. Again, let me mention it again. Present state is A. Yes, sir. Present state is A. With input x is equals to 1. Next state is C. With input x is equals to 1. Next state is C. And what is the output? Output is 0, sir. With input x is equals to 0. Present state is A. With input x is equals to 0. Next state is B. Output 0. So next state is B. Output 0. Is it okay? Great, sir. Again observe present state B. Present state is B. With x is equals to 1. Next state E. Output 0. Next state E, output 0. Next state E, output 0. With present state B, x is equals to 0. Sorry. That is for 1. X is equals to 1. I have mentioned here for x is equals to 1. X is equals to 1. E, output 0. Okay. Present state B. X is equals to 0. Next state D, output 1. D, 1. Now, present state C. Present state C. With x is equals to 0. Present state C. With x is equals to 0. Present state C. With x is equals to 0. Next state is again C only. And what is the output? 0. So C, 0. Present state C. With x is equals to 1. Next state D. Output 1. D, 1. Present state D. X is equals to 0. Next state A. Output 0. Next state A. Output 0. Next state A. Output 0. Present state D. X is equals to 1. Next state D again. Output 0. D, 0. Yes, sir. Present state E. X is equals to 1. Next state D, output 1. X is equals to 1. For x is equals to 0. C, output 0. Now please observe. Is any two different conditions which are giving the same output and same next state for every possible input? Now observe. If you observe this row, and this row, then the two rows will have same input, same output for same input for all same inputs. Okay. However, this is for E and this is C. So these two will have same next state for a same input condition and same output. So we need not to represent these two different. We can remove any one of them. One of them is a redundant one. Is it okay? Yes, sir. So out of C and D, you can remove any one to reduce the state diagram. So I am interested to construct a reduced state table. This is your state table. Obtained from the state diagram. Then I am interested to write reduced state table. Now how to write the reduced state table? Very easy, sir. In a reduced state table, you can remove. Now for a reduced state table, you can remove either C or E, because the two are giving same output for same input conditions. Because the two are giving same output for all possible same input conditions. Okay? Yes, sir. So now please observe here. We have a present state. Yes, sir. Next state with x is equals to 0, x is equals to 1. Okay? Yes, sir. And output y with x is equals to 0 and x is equals to 1. Is it okay? Yes, sir. Because C and E are same. So any one of them can be removed. Is it okay? Now you know, sir, in case if we have to implement, then how many number of states we have? 5. For five number of states, minimum bit required will be 3, and for 3 minimum bit, 3 flip-flops are needed. But it can be clearly observed that states C and E are giving same next state for the same input condition with the same output. So we need not to represent these two. Instead of taking C and E as a two different, we can treat it as a same state. Is it okay? That makes the number of state only 4 and number of flip-flops needed only 2. So this is the reduction in states. With the reduction in state, the cost of the circuit reduces. Great, sir. So now please observe here. I am replacing E by C. Okay. So we have A, B, C, D only. Yes, sir. We can represent it like, if we have A, then for x is equals to 0, B 0, C 0. Great, sir. D, instead of writing E, I am writing C. I am replacing C. I am replacing E by C. I am replacing E by C. Replacing E by C. Okay? Yes, sir. Great. So when I am replacing E by C, then I need not to represent your last row, E row. Okay? Then again, this will be 1, 0. Yes, sir. Then C, D, 0, 1 and 0, D, 0, 0. This is your reduced state table. For this reduced state table, we can construct a state diagram. For this reduced state table, we can construct a state diagram. So I am going to construct a state diagram now for this state table. Is it okay? Yes, sir. So now please observe here. We have total how many number of states? 4. A, B, C and D. So we have total 4 different state. Now if state is A with x is equals to 0, next state is B. Output 0. 1, next state is C. Output 0. With 1, next state is C. Output 0. Present state B. X is equals to 1. Next state D. X is equals to 0. Next state D. Output 1. Yes, sir. Present state B. X is equals to 1. Next state C. Output 0, sir. Present state C. X is equals to 0. Next state C only, sir. Output 0, sir. Present state C. X is equals to 1. Next state D. Output 1, sir. Present state D. X is equals to 0. Next state is a C, sir. This is C basically. Sorry, A. Next state is A. It is A. Yes, sir. So next state is A. Output 0, sir. Present state is D with x is equals to 1. Next state is D only, sir. D only, sir, and output 0, sir. So this is your reduced state diagram. Hoping now you are able to understand how to write the reduced state table and how to find reduced state diagram. How to construct a reduced state diagram and what is the benefit of state reduction in our state machines, finite state machine. Is it okay? Now we have a basic idea of state machine, state reduction, as well as Mealy and Moore model. Okay. Now I am interested to use this Mealy and Moore model to design some practical circuit. So for that we generally used a sequence detector. What is the purpose of sequence detector? That is used for data transmission as well as used for data transmission or receiving. Okay. So digital communication, majorly it is used in the digital communication. Is it okay? Yes, sir. Great. Now please observe this, very important, mostly used in digital communication. Nowadays digital communication is a very important part. We can't imagine our mobile phone, our internet, even this class without a digital communication. So now I am going to move towards the digital communication. Up to this part, the use of digital communication like sequence detector. So please let me know up to this part everything is clear. If you have any issue with anything, please feel free to ask. Okay, great. Please observe what is sequence detector. As the name suggests, which can detect some specific sequence. Sequence detector is a sequential circuit which can detect for some specific sequence of consequences. Is it okay? When I am saying consequences, definitely it means in terms of digital as 0, 1. Okay, sequence of 0, 1. Now please observe. It is used to detect the input sequence in a clocked synchronous sequential circuit. Sequence detector is used to detect input sequence in a clocked synchronous sequential circuits. Great, sir. It is mostly used in digital communication to detect the message. Mostly used in digital communication to detect message. Yes, sir. Great. Now please try to understand. This is your sequence detector. So how it works? We are going to give the input here, maybe 1 bit, 2 bit or 3 bit. So presently I am representing X a 1 bit input here. Is it okay? We are getting Y as a 1 bit output here, and on application of clock we are getting this output Y. Is it okay? Yes, sir. Output Y will become logic 1 only when the sequence is detected. When the input sequence is detected. When the input sequence is detected, then output Y will become logic 1. Okay, sir. Let us suppose we need to detect a sequence 1101. We need to detect a sequence 1101. Please observe here. We need to detect a sequence 1101. We need to detect a sequence 1101. Please wait. Let us suppose we need to detect a sequence 1101. So when I am saying 1101, it means what? 11 1101. Now please observe. We have to detect a sequence 1101. So this is your input, that is X 1 1 0 1. On application of clock, if it is getting that sequence, on application of first clock, this is input X is 1. On application of second clock, input X is 1. On application of third clocks, input X is 0. And on application of fourth clock, input X is 1. Then it indicates output is set to be logic 1. Output is set to be logic 1 when the sequence is detected. Till the sequence is not detected, output will remain low. Soon as the sequence detected, output will become logic 1. Soon as the sequence detected, output will become logic 1. Is it okay? Sir, we are unable to understand this. No, no, no. You are able to understand. You need to understand it again. Please see. I'm saying we are interested to design a sequence detector which can detect a input sequence 1101. Now, if you observe an input X 1101, so till the sequence is not detected, output will remain low. As soon as the sequence detected 1101, soon as the sequence detected, output will become logic. This gap I have made in order to show you the propagation delay. Okay? Yes, sir. Great. Now, please try to understand. Sequence detector can be designed in two different ways. Sequence detector can be designed in two different ways. First one is non-overlapping sequence detector, and the second one is overlapping a sequence detector. Overlapping sequence detector can be a 1-bit overlapping, or it can be a 2-bit overlapping. It can be a 1-bit overlapping, or it can be a 2-bit overlapping. Is it okay? Yes, sir. Okay. Maybe 1-bit, 2-bit, or a 3-bit overlapping. Okay. Now please observe here. First, I want to discuss about the non-overlapping. First, I am interested to know about the non-overlapping. Non-overlapping means what? Please observe here. Non-overlapping sequence detector. So we have a sequence detector here. Please try to understand this. This is a clock. Yes, sir. These are the input X. Yes, sir. And this is your output Y. This is your sequence detector. Okay. Okay, sir. Now, let us suppose we are interested to design a sequence detector as 1101. You can design it for any count sequence, for any sequence. It is not mandatory that you have to design it for 1101 only. You can design it for 1011 also. Anything. Okay. So let us take an example of 1101. So I'm interested to detect this sequence 1101. Okay. Yes, sir. Now the inputs are coming as 1101101011010, anything. In the input it is coming. Let us suppose the input is coming as 1101, 1101, 1101, and so on. Is it okay? Yes. So this is the case of non-overlapping. So when the first input appeared, then whether the output sequence is detected? No, sir. Output sequence is set to be detected when we will get the sequence of 1101. So sequence is not detected, output is 0. Sequence is not detected, output is 0. Sequence is not detected, output is 0. At this case, at this particular condition, sequence detected, so output will become logic 1. Is it okay? This indicates the sequence got detected 1101. The sequence which is needed to be detected, the same sequence is appearing. Now again observe 1, 1. So sir, 0, 0, 0, 1. 1101. Whenever sequence got detected, output will become logic 1. Again observe here 1101. So sequence will be detected here. So the output is going to be high under these conditions. So output will becoming high only when the sequence got detected. Is it okay? Yes, sir. This is a 1-bit non-overlapping sequence detector. Hoping you are able to understand. Non-overlapping. Now let's talk about overlapping. Overlapping may be of by 1 bit, maybe by 2 bit. So let us now discuss about the overlapping sequence detector. So let us talk about the overlapping. Overlapping may be a 1 bit, maybe by 1 bit or 2 bit. So in case of non-overlapping, we know that. Now let's talk about overlapping. Let the required sequence will be 1101. We need to detect a sequence 1101. Okay, yes, sir. We need to detect a sequence 1101. But this is a overlapping sequence detector. This is a overlapping sequence detector. Okay. So this is your input X and your output Y. This is your overlapping sequence detector. So overlapping sequence detector. Please observe here. 1101 sequence got detected. Whenever sequence got detected, output will become logic 1. Now in case of overlapping, in case of 1-bit overlapping sequence detector, the last bit of the previous sequence will become first bit of the next sequence. So now again you have to observe from here. Yes sir. So sequence not got detected here, the sequence got detected 1101. In case of 1-bit overlapping, the last bit of a sequence is the first bit of the next sequence. Last bit of a sequence is the next bit of the next sequence. First bit of the next sequence. So 1101. Sir, here your sequence got detected, so this will become 1. It is different from the previous one. In case of non-overlapping, the output is different. In case of overlapping by 1 bit, the output is different. Is it okay? Great, sir. Let's talk about overlapping by 2 bit. A sequence detector overlapping by 2 bit. So a sequence detector overlapping by 2 bit. Let us suppose we need to get the required sequence as 11011. Okay? Yes, sir. We need to get the output sequence as 11011. Okay, we have clock here. Yes sir. Input X and output Y. This is a 2-bit overlapping sequence detector. Okay. Yes sir. So for a 2-bit overlapping sequence detector, please observe the last 11011. This is the required sequence. Soon as the required sequence will got detected, output will become logic 1. Is it okay? Yes sir. Now please observe, in case of a 2-bit, in case of a overlapping by 2-bit, then last 2-bit of the first sequence will become first 2-bit of the next sequence. So now you have to observe from here. Again you can say, sir, whenever sequence got detected, output will become logic 1. The last 2 bits of the first sequence is the input bits of the next sequence. Is the input first 2 bits of the next sequence. So 11011. 11011. It means sequence got detected. Output will become logic 1. Again observe from here. You can say, sir, whenever output sequence is detected, output will become logic 1. So this is how we can write the overlapping by 2-bit. Is it okay? Now let's discuss about the note point. We can design a sequence detector by using Mealy machine or by using Moore machine. Basic difference that we need to remember is, if we have to design a sequence detector of n bit or for n bit, then the number of states required in Mealy machine is equals to n, while the number of states required in Moore machine is n plus 1. One extra state is needed always in case of Moore machine. One extra state is required comparative to Mealy in case of Moore machine. Is it okay? Yes, sir. Now please observe first how to construct a sequence detector by Mealy model. Okay. For Mealy model, we have to follow some important points. Please see. First one, maybe we have to design a non-overlapping or overlapping by 1 bit or overlapping by 2 bit. So in case of non-overlapping, move the last bit when sequence is detected to the reset state. Move the last bit to the reset state. When sequence is detected, move the last bit to the reset state. Later on I will show what is that. Just note down. Second, in 1-bit overlapping, compare the last bit to 1-bit state. In case of 1-bit overlapping, compare the last bit to 1-bit state. In case of 2-bit overlapping, compare the last bit when sequence got detected with a 2-bit state, and then 1 bit with a 1-bit state, and so on. Okay. Sir, we are unable to understand these. Okay, just write down. Later on I am going to discuss it again. Please just write down. Whenever we have to design a sequence detector by using Mealy model, we are going to follow some steps. Step number 1, in case of non-overlapping, move the last bit to the reset state. In case of 1 bit overlapping, compare the last bit with a 1 bit state when sequence got detected. In case of 2 bit overlapping, compare the last bit when sequence got detected with a 2 bit state, and then 1 bit with a 1 bit state, and so on. Great. Now please observe. First I am taking a consideration of non-overlapping. For any sequence you can write. I am just taking 1 0 1 0 1 1. You can take any sequence. You can take 1 0 0 1 0 0 1 sequence. You can take 1 1 0 0 sequence. Anything. Okay. Yes, sir. So let me take non-overlapping. Non-overlapping. This is a Mealy model. I am interested to design a Mealy model. Okay. So non-overlapping Mealy model. So how many number of bits in the sequence? First of all, you have to identify the number of bits in a sequence. How many number of bits in a sequence? Sir, there are total 4 bits. The number of bits in a sequence can be defined the number of states. So how many number of states are there? Sir, 4 states are there for a Mealy model. For a Mealy model, number of bits is equals to number of states. In case of Moore model, number of bits is equals to number of states is equals to number of bits plus 1. Okay. So this is a Mealy. For Mealy, you can say, sir, number of bits is equals to number of states. So how many number of states are there? So they are required. The required number of states are 4. So 4 states are required. 1 0 1 1. This is the sequence detector I am interested to design. For that, first of all, I have to design a state diagram. Once I have a state diagram, I can construct a state table. Then from the state table, I can construct a excitation table. From the excitation table, I can find the excitation needed onto the flip-flop. And now my sequence detector will be designed with the desired flip-flop. Great, sir. So first of all, I'm just giving the state name as 4 different states. So I'm just giving the name as A, B, C, D. This first state, we always treat it as reset state. Reset state means 0 0 0 0 state. Okay. Yes, sir. So this is your reset state. Now please observe here and identify what is the sequence needed. What is the sequence needed? If the present state is A and we will get the input 1, all the sequence are not yet detected, so output is a 0, but we are getting the required sequence of first bit, so move to the next state B. Is it okay? Yes, sir. Now, if you are in state B and if the input now coming as x is equals to 0, then move to the next state C. Since all the states are not yet detected, so write output to be 0. Great, sir. Now next is if you are at state C and input x is equals to 1, then move to the next state D, because you are getting the required sequence, but all the required sequence is not yet detected, so write output is equals to 0. Now you are on state D. State D will be moved to state reset state only, but we will later on see how it will move. First, please observe. Now please observe, I am trying to show you different bits. Like this is your 1 bit position, state B. This is your 2 bit position, state C. And state D is your 3 bit position. Okay. Yes, sir. So after 3 inputs, I am saying 3 bit position, just in order to understand how to design. Okay. Now, when you are on state A, then input may be possible 0 or 1. In case if 1 is coming, it means it is in the required sequence, you will move to the next state. But what happened if 0 as an input received, you will remain in the same state. If 0 is received, you will remain in the same state A. Now, 1 bit is detected. When x is equals to 1, then 1 is the required, this x is equals to 1, it means 1 bit got detected. Soon as 1 input bit got detected, now you are onto the 1 bit state. You are onto the 1 bit state, it means at B 1 bit is detected of the required sequence. Now, from B, you can either apply the input x as 0 or 1. If you are applying 0, then it means you have 2-bit detected. So you will move to the next state. But in case if x is equals to 1 coming, then in case if x is equals to 1 coming, then you need to compare the last 1 bit to the 1 bit position. If last 1 bit to the 1 bit position is the same, if last 1 bit to the 1 bit position is the same, then be on to the same state, otherwise move to the reset state. So since last bit is equals to 1 bit state, so be on to the state B only, and this is appeared when x is equals to 1, sequence not detected, so output is 0. Great, sir. Further, if x is equals to 0, then state in a sequence, 2 bits in a sequence got detected. So you have reached to the 2-bit state. Now you are on to the state C. With x is equals to 1, x is equals to 0, you have reached to state C. On state C, again, there are two possibilities of the input x. X may be 0, may be 1. In case if x is equals to 1, then required sequence will be detected. You can move to the next state. Yes, sir. You can move to the next state. But in case if x is equals to 0, then this is not the required state. Now compare these last 2 bit with a 2-bit state. If it matches, remain on to state C. If it doesn't match, then compare last 1 bit with a 1-bit state. If it matches, come to state B. If it doesn't matches, then you are going to reach to state reset only. So in case if you are at state C and x is equals to 0, input appeared, then again you will reach to the reset state with the output 0. Output will become 1 only when all the bits in the sequence got detected. Great, sir. Now again we are at state 101. Now we are at state 101. 101 is the 3-bit state, that is state D. In case if 101, if x is equals to, now if input x is equals to 1, then you can say, sir, all the states are being detected. When all the states are being detected, move to the reset state. When all the bits are being detected, move to the reset state with output x is equals to 1, with output y is equals to 1. All the states are being detected. But in case if you are getting 1 0 1 0, if you are getting 0 onto the last one, then it is not the required sequence. Yes, sir. When it is not the required sequence, then first of all you have to identify whether it will stay on the same or return back to the previous one. Sir, in case if this will be 0, it means the required sequence is not got detected. Since it is not a overlapping, so we need to come to the reset state again with x is equals to 0 and output 0. Please observe here, I have already shown to you, in case of non-overlapping, move the last bit to the reset state. Now when sequence is detected, output is 1. When sequence is not detected, output is 0. But it will be moving to the last bit only. Is it okay? Similarly, in case of 1-bit overlapping reaches to 1-bit state, 2-bit overlapping reaches to 2-bit state, and so on. Great, sir. Great, sir. Great, sir. So now you know how to construct a state diagram for a sequence detector. In case of Mealy machine, the condition is non-overlapping. Let us talk about the overlapping also. Let us talk about 1-bit overlapping. Let us talk about 1-bit overlapping. Okay. So 1-bit overlapping. Suppose we need to detect the same sequence 1101. I'm interested to detect the same sequence 1101. Okay. So how many number of states are there? 4 states are there. Why? Because there are 4 bits in the sequence. So number of bits is equals to number of states in case of Mealy. So I am representing 1-bit overlapping in case of Mealy model. Great, sir. In case of Mealy model. Great, sir. So now please observe here. Present state is A. In case if If input x is equals to 1, you will reach to the next state. Yes, sir. Output is 0 because all the sequence is not got detected. First take the sequence and draw up to the final state. Okay. So if the state is B and input 1 is appeared, then move to the next state. Final output is not yet detected, so output is a 0. Then again move to the next state. Sir, again move to the next state in case of 0, but all the states are not detected, so output is a 0. Last one, keep it. We will talk about the last one also. This is a 1-bit state. Yes, sir. This is a 2-bit state. Yes, sir. And this is a 3-bit. Okay. Great, sir. Now please observe. If A is equals to, if the present input x is equals to 0, then if you are at state A and you are receiving x is equals to 0, it means the required sequence is not got detected. So you will remain in state A and output is 0. Is it okay? Yes, sir. Now, if you are reaching to state B, it means 1 bit in the sequence got detected. We have to detect a sequence 1101. So 1 bit in a sequence got detected. Okay. Yes, sir. Now, input x can be 0 or 1. Input x can be 0 or 1. In case if input x is 1, then both the bits are detected. So you can go to the 2-bit state. Yes, sir. However, in case if x is equals to 0, then it is not the required sequence. We need to required sequence as 1101. So the required sequence is not available. Now we need to compare the 1 bit to the 1-bit state. If they are same, you can say it will remain in the same state. But if x is equals to 0, then you can observe this last bit is not equals to 1-bit state. So it will return to the reset state. So if present state is 0, present input coming is 0, then it will return to the reset state with the output 0 because the pattern is not yet detected. Output will become logic 1 only when the pattern got detected. Okay. Yes, sir. Now, if x is equals to 1, then you have reached to the C. It means 2-bit got detected. At this particular state, 2-bit in the sequence got detected. As per the desired sequence, we have detected 2 bits. Now, again, x may be 0 or 1. If x is 1, if x is 0, then you can say, sir, required bit is detected. So you can move on to the next state. Yes, sir. You can move on to the next state. So if x is equals to 0, you can say moving from C to D state. But if x is equals to 1, then this is not the required sequence. So we need to first compare the last 2 bit with a 2-bit state. If they are same, it means it will remain in the same state. If they are different, then it goes to the then we have to compare the 1 bit with the 1-bit state. If they are different, then we have to put that state from state C, we have to return back to state A only, reset state only. Is it okay? Yes, sir. Great. So this is where the x is equals to 1 and output is, sir, 0. Now, state D. Up to the D state, all 3 bits in the sequence got detected. Now, this x may be 0 or 1. It means input x may be 0 or 1 and the present state is D. If input x is equals to 1, then all the states got detected. In case if all the states got detected, then in case of a 1-bit overlapping, in case if all the bits are detected, then compare the last bit to the 1-bit state. Compare the last bit to the 1-bit state. Compare the last bit to the 1-bit state. Yes, sir. They are same. It means you are reaching here. Is it okay? Yes, sir. So 1, 1. All the sequence got detected. However, if 1, 1, 0, if you are getting 0, now again you have to compare these 3-bit with these 3-bit, then compare these 2-bit with the 2-bit state, then compare 1 bit with the 1-bit state, and then compare. If it is not satisfying 1 bit with the 1-bit state, then it goes to the reset state 0, Is it okay? So this is how you can construct a state diagram. All the difficulty is only up to the state diagram. Once the state diagram is designed, then it will be very easy to construct a sequence detector. Very easy to construct a sequence detector. Is it okay? Great, sir. Now come to the 2-bit overlapping. Again, I am trying to show you 2-bit overlapping also. Okay. Please observe, in case of 2-bit overlapping. In case of 2-bit overlapping. Okay. So let's take a question. Like we have to, let us suppose we have to detect a sequence 11011. We have to detect a sequence 11011. So how many number of states are there? Sir, how many number of bits? Total 5 bits. So how many number of states for Mealy model? Sir, for Mealy model, we need 5 states. Is it okay? Yes, sir. 5 states. So I am naming the states as A, B, C, D, E. Where A I am treating as a reset state, it means 00 state. Okay? Yes, sir. Now, what is the sequence? If the input X is equals to 1, we reach to the next state, output 0, because the sequence is not detected. If the state is B and again 1 input is coming, then next state is C. If 0 is coming, next state D. If 1 is coming to the input, the next state is E. Output 0. Now, up to this part is okay, sir. Again, in order to understand overlapping, I am showing you 1 bit state, then 3-bit state, and 4-bit state. Okay. Okay, sir. So now please observe here. First of all, I am discussing this A state. State A is a reset state. Okay. There is a 2 possibility onto state A. Maybe if you are on state A, input maybe 0 is coming or input maybe 1 is coming. So if input 1 is coming, then 1 is the required sequence. So you have to move to the next state. But if input 0 is coming, then it will remain in the same state with the output 0 because the sequence is not detected. Now please observe, when we have reached to the state B, it means 1 bit is already detected in the sequence. X can be 0 or 1, X can be 0 or 1. If X is 1, then the 2 bits are detected, you have to move to the next state, C. If X is equals to 0, then the required sequence is not got detected. So in that particular case, we have to compare the last bit with the 1 bit state. If it matches, then it will remain onto the state B. But if it will not matches, return back to the state A. So sir, 0/0. Why I am writing? When X is equals to 0, present state is B, X is equals to 0, next state is A, and output is 0 because sequence is not detected. Is it okay? Great, sir. Now let us suppose you are on state C. When you have reached to state C, it means 2 sequences, 2 bits are in the sequence got detected. Now there may be a possibility of 1 X is equals to 0. If X is equals to 0, it means all the 3 bits in the sequence got detected. So you have to move to the next state D. But in case if X is equals to 1, then the state is not detected. Now you have to compare the last 2 bit with the 2 bit state. If they are same, you will have to remain in the same state. So 1/0. 1 is the input state and 0 is the output. Output will remain low till all the sequence got detected. Great, sir. Now again observe, if you are getting X is equals to 0 onto the state C, it means 110 is detected in the sequence. You have reached to the 3-bit state. Now in a 3-bit state, I'm just giving the name it as a 3-bit state. All the states will have same number of bits. It is just in order to understand the topic, I'm just saying it as a 3-bit state. Now up to this 3 bits got detected. So now again X will have 2 possibility, maybe 0, maybe 1. If you are on state D and you will get X is equals to 1, it means in the sequence 4 bits got detected. So you have to move to the next state E. Yes, sir. However, in case if X is equals to 0, then your states not got detected. Your required sequence is not detected. Under this condition, you have to compare the 3-bit with the 3-bit state. If it matches, remain on to the state D. If it does not matches, then compare last 2-bit with the 2-bit state. If it matches, come to the state C. Otherwise, compare last bit to the 1-bit state. If it matches, come to the state B. If it does not matches, then return back to the state A only. Is it okay? Yes, sir. What is the condition? X is equals to 0, output 0. Is it okay? Up to this part, everything is clear, sir. Come to state E. Up to state E, how many sequence detected? 4 bits in a sequence got detected. Now only we have to detect the 5th bit. Now there are two possibilities with the input X. Input X may be 0, may be 1. So in case if input X is equals to 1, it means all the bits in the sequence got detected. In case if X is equals to 1, then all the bits in the sequence got detected. So in case of 2-bit overlapping, compare the last 2-bit to the 2-bit state. If it matches, come to the 2-bit state. Otherwise, compare the last 1-bit to the 1-bit state. If it matches, come to that particular state. Is it okay? Yes, sir. So now please observe here. This is your 2-bit overlapping. Yes. So compare the last 2-bit with the 2-bit state. It is matching. Yes, sir. So come to the 2-bit state. The C state is your 2-bit state. Is it okay? Yes, sir. So this is when input X is equals to 1, output is 1 because all the sequence got detected. However, in case if 11010 is coming, now where you have to reach, you need to compare the last 4-bit, last 3-bit with the 3-bit state. If it matches, come to the 3-bit state. If it doesn't matches, then compare last 2-bit with the 2-bit state. If it matches, come to that particular state. Otherwise, compare last 1-bit with the 1-bit state. If it matches, okay, come to that state. Otherwise, come to the reset state. This is when 0/0. So this is how you can construct a state diagram for a Mealy model for overlapping of 1-bit, 2-bit, or now you can design any number of bits, overlapping of any number of bits. Is it okay? 1-bit overlapping or 2-bit overlapping. Is it okay? Yes, sir. Because its base is 2, so it comes up to 2-bit overlapping. In the sequence, maybe 2 same bits will come. Yes, sir. Up to here, I am hoping you are able to understand. Great, sir. Next is your Moore model. Let us talk about Moore model. Okay. So for Moore model, let us suppose I have to construct a state diagram for a Moore model. Now please try to understand. Very important topic. Very easy to understand. Now let's talk about Moore model. In a Moore model for 4-bit sequence, okay, construct state diagram for sequence detector. Construct a state diagram for sequence detector. Construct a state diagram of Moore model. Construct a state diagram for sequence 1101. Let us take this one. Okay. Construct a state diagram for the sequence 1101 in Moore model. For 4-bit sequence, 5 number of its states are required. Why? Sir, always for n bit we required n plus 1 states in case of a Moore model. Now please observe how to represent a Moore model. So we have a state A, B, C, D and E. There are total 5 states. Okay, sir. Now please observe here. Now please observe here. Input sequence is appearing. So if input is 1, then from state A you will reach to the next state because one bit in the sequence got detected. Otherwise you will remain in the same. Since all the sequence are not detected, so output is a 0. So this is your input and output. Is it okay? Yes, sir. Now please observe here. From B, if input x is equals to 1 appear, you will reach to the next state, but all the sequence not detected, so output is a 0. From C, if 0 x is equals to 0, you will reach to the next state because in a sequence input is detected but entire sequence is not detected, so output is a 0. Now if x is equals to 1 and you are on state D and go to state E, but still your output is a 0 because all the sequence are not yet detected. Is it okay? Yes, sir. Now at that particular input condition, at that particular state 1 1 0 1, all the states are being detected, so output will become 1. Is it okay? So this is how we have to represent the Moore model. Now please observe, I am interested to construct the entire state table. So 1-bit position, 2-bit position, 3-bit position and 4-bit position I am representing. Let us suppose we are on state A. If x is equals to 0, it will remain in state A, and if x is equals to 1, it reaches to state B. Yes, sir. Great. So 1 bit is detected. Now 1 bit is detected. Next, x may be 0, may be 1. In case if x is 1, then 2 bits are detected, so it reaches to next state C. Yes, sir. In case if x is equals to 0, then sir, now these two are not in the desired sequence. So under this condition, you need to compare 1 bit to the 1 bit state. If it matches, remain on to the state B. If does not matches, then come to the state A, that is reset state. So this is when x is equals to 0. Is it okay? Great, sir. Up to state C, 2 bits are already detected. 2 bits in the input sequence are already detected. Now again detect x. Again detect the next bit. If x is equals to 1 is coming, if x is equals to 0 is coming, then all the 3 bits are detected. Go to the next state. In case if x is equals to 0 is coming, in case if x is equals to 1 is coming, then it is not the required state. Now compare the last 2 bit with the 2-bit state. If it matches, come to that state. If it does not matches, then compare 1 bit with the 1-bit state and compare 0. Otherwise, just put it draw a state from C to reset state. Yes, sir. So here 2-bit, last 2-bit matches with this 2-bit state. So remain in the 2-bit state with x is equal. Great, sir. Again, up to the state D, 3 bits are being detected already. Now we have to detect the fourth input bit. So 1 1 0. In case if 1 is appear, all the states are being detected. Go to the next state. In case if x is equals to 0, then in case if you are getting x is equals to 0, then you need to compare the 3-bit with the 3-bit state. If it matches, remain on the state. Otherwise, compare the last 2-bit with the 2-bit state. If it matches, come to the 2-bit state. If it does not matches, then compare 1 bit with the 1-bit state. If it matches, come to the 1-bit state. If it does not matches, then go to the reset state. Great, sir. So it means if we are getting 1 1 0 0, then go to the reset state again. In case if we are getting 1 1 0 and then x is equals to 1, go to the next state. All the bits in the sequence got detected, so output will become 1. Is it okay? Yes, sir. This is a Moore model. Now in the Moore model, we have to follow some certain conditions or set of rules. Now please observe how to consider the last one based on this theory. Please observe, whenever you are designing, whenever you are constructing a state diagram by Moore, then first observe whether the case is of overlapping or non-overlapping. So this is the case of non-overlapping. Is it okay? I am constructing a state diagram for the sequence this by Moore model. non-overlapping. Is it okay? Yes, sir. So in case of non-overlapping, what we have to do? In case of non-overlapping, Moore model, compare the last bit to 1 bit state. Compare the last bit to 1 bit state. Is it okay? Yes, sir. When sequence got detected, compare the last bit to 1 bit state. When sequence got detected, compare the last bit to 1 bit state. Compare the last bit to 1 bit state. And if it matches, come to this state. Is it okay? Yes, sir. With x is equals to, now we need not to apply any. Is it okay? Yes, sir. So again, we need to start it from here. Great, sir. Last bit with the last bit state. With x is equals to, with again x is equals to 0 or 1. Is it okay? 1, 1, 0, 1. Now, if this is 1, then compare the last bit with the last one bit state, and if it matches, you have to go there. If it does not matches, let us suppose we are getting 1, 1, 0, 1, 0. If we are getting x is equals to 0, it means last bit is not matching with the sequence. If last bit is not matching with the sequence, where we have to go? If last bit is not matching with the sequence, it means we have to go to the last 3 bit with a 3 bit state, last 3 bit with a 3 bit state, then last 2 bit with a 2 bit state, 1 bit with a 1 bit state, and a 0 bit. So it is coming here, case of 0. Again, it is going to be started from the same. Is it okay? Great, sir. So this is how we can construct a state diagram for the sequence detector in case of Moore model. In case of Moore model, since the last bit, we have to compare the last bit with the 1 bit state. In case of non-overlapping, in case of overlapping, 1 bit, compare last bit with the 2 bit state, and then 1 bit with the 1 bit state. Overlapping with the 2 bit, then compare the last bit when sequence detected to the 3 bit state, then 2 bit with the 2 bit state, and so on. Is it okay? Now hoping you are able to understand how to construct the sequence, how to construct the state model, state diagram of the sequence detector. So now I am going to design one sequence detector for you, okay, so that you will be able to understand how to design any sequence detector. Okay, now please see, what is sequence detector? Again, sequence detector is the sequential logic circuit that can be used to detect the arrival sequence of the bits at data input. So sequence detector is used to detect the input sequence only. We have X as an input, Y as an output, and clock pulse. I am interested to design this sequence detector now for any specific sequence. What is the procedure? First, we have to follow some set of rules to design any sequence detector. Now we know each and everything. From the starting of the class, the main motto is to understand how to design a sequence detector. And now we have reached here, how to design a sequence detector. Now we know about the state reduction. Now we know about the state table. Now we know about the state diagram. Now we know about how to draw the state diagram for a non-overlapping as well as overlapping state sequence detector. Is it okay? Great, sir. Now please observe here, very important, please observe here, very important. The number of states in the state diagram is equals to number of bits in the sequence. So let us suppose we have to design a 6-bit sequence detector. So if we have a 6-bit, it means we need to design a 6 number of different state for Mealy model and 7 number of different state for Moore model. Okay? Yes, sir. Then draw the lines, directions between the states of the inputs and output. Draw the line directions between the state of the inputs and outputs. Then state assignment. So we need to assign the states and construct state table. State assignment and construct state table. Draw excitation table. Then use K-map for simplification of the excitation table. And at last, you need to implement the logic circuit. Is it okay? Yes, sir. So first, find the number of states, then draw the state diagram. After state diagram, do the state assignment, A, B, C, D, so on. And then later on, draw the excitation table. From the excitation table, you will get the excitation equation. Use K-map to find the minimized excitation equation and then implement the logic circuit. So we need to go with these 5 states, these 5 steps only. 6 steps only, okay? Now please observe here. Let's take an example. I'm interested to draw some sequence, one sequence detector, okay? So let's take an example of a sequence detector. Design a sequence, design a non-overlapping, I'm taking the concept of non-overlapping. In the same fashion, you can now design anything, overlapping or non-overlapping, okay? Design a non-overlapping sequence detector to detect the sequence 1000011 by using Mealy machine using JK flip-flop. By using Mealy machine using JK flip-flop. You can use D flip-flop, you can use T flip-flop. Presently, I wanted to know about the JK flip-flop because just one question makes you able to understand all the concepts. Okay. Now please observe here. First of all, we need to design a state diagram. How many number of bits are there? Sir, 1, 2, 3, 4, 5, 6. So please observe here. For 6 bit, 6 bit, number of states is equals to 6. Is it okay? Yes, sir. So first is to find the number of states. Next, we need to draw the state diagram. So I am going to draw the state diagram. Now 6 different states. So I am representing here A, B, C. Oh, it will be quite difficult to show in this way. Just representing A, B, C, D. A, B, C, D, E. 5, 6. So we have total 6 different states. Now first of all, you have to draw the if the input is obtained in the sequence, then you have to draw the next state first. Okay. So if you are on state A, if you are getting input X is equals to 1, which is in the sequence, but yet not all the sequence detected, move to state B. Now if you are on state B and input X is equals to 0 is up here, then move to the next state C. Output remain in the 0 state because the entire sequence is not yet detected. If the input is a 0, then move to the next state because 0 is the required sequence. 0 is the required sequence. So move to the next state, and output is 0 because the entire sequence is not yet detected. If you are on state D and X is equals to 0 appear again, 1, 0, 0. Then again, if a 1 appear, move to the next state. If 1 appear, move to the next state. Is it okay? Yes, sir. Output, sir, 0 because all the states are not detected. Output 0 because all the states are not yet detected. Is it okay? So 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. Till this, I'm hoping everything is clear. Yes, sir. Great. Now, at the first, if you are on reset state and X is equals to 1 appear, you will reach to the next state B. In case if X is equals to 0 appear, then you will remain onto the reset state. This is what we call reset state. Is it okay? Now come to the 1-bit state, then 2-bit state, 3-bit state, 4-bit state, and 5-bit state. Please observe here. If input x is equals to 1, then 1 bit is being detected. Now come to the x. There are two possibilities. X may be 0, may be 1. In case if x is 0, move to the next state. However, in case if x is equals to 1, then you have to compare this one with the 1 bit. If it is same, it will remain in the same state. Otherwise, it will return back to the reset state. Yes, sir. So x is equals to 1, then it will remain in state B only. Now, if x is equals to 0, you have reached to the 2-bit state because 2 bits are being detected. Now, if next c is equals to 0, you will reach to the next state. Yes, sir, that is 1, 0, 0. But in case if x is equals to 1, then that is not the required sequence. Now you have to compare the last 2-bit with the 2-bit state. If it matches, remain on to the 2-bit state. If it not matches, then compare the last 1 bit with the 1-bit state. If it matches, come to that state. So, sir, it will be again coming back to the state B with x is equals to 1, output 0. Great, sir. Now, up to this state D, 3 input bits are detected in the sequence. 3 input bits are detected in the sequence 100. Again, there are two possibilities of x. X may be 0, may be 1. If x is 0, then all the 4 inputs are being detected. 4 input sequence are being detected. So move to the next state E. In case if this is 001, then this is not the required sequence. Compare the last 3-bit with the 3-bit state. If it matches, remain on to the 3-bit state. If it does not matches, compare the last 2-bit with the 2-bit state. If it matches, come to that state. If it does not matches, then compare last 1-bit with the 1-bit state. If it matches, come to that state. Otherwise, go to the reset state. So, sir, we have onto the state D with x is equals to 1. We have reached to the state B again. Output is 0 because the sequence is not yet detected. Again, we have reached here. X is equals to 0 or 1 is possible here. If x is equals to 1, then it is the required sequence. You can move to the next state F. If it is 0, then it is not the required state. Now compare these 4 with the 4-bit state, compare 3-bit with the 3-bit state, compare 2-bit with the 2-bit state, compare 1-bit with the 1-bit state. If it does not matches, then come to the reset state. So from E, it come to the reset state. In case if 0 appear, output is 0. Now we have the last F. Again observe here x. In case if x is equals to 0, in case if x is equals to 0, now please observe, in case if x is equals to 0, the sequence not get detected. Yes, sir. If the sequence will not detected, then sir, compare the last 4-bit with the 4-bit state, then compare last 3-bit with the 3-bit state, then compare last 2-bit with the 2-bit state. So, sir, yes, it is going to be matches with the last 2-bit with the 2-bit state. So come to the 2-bit state. 1, 0 is a 2-bit state C. Okay. So for 0, you are getting output 0. If we are getting 1, then move to the first bit state. If we are getting 1, then move to the reset state with the output 1 because all the sequence got detected. So this is how you have to construct a state table first. So now you know how to construct a state table. Yes, sir. It's a non-overlapping case. Yes, sir. Now we have a state table. Now we have a state diagram. From this state diagram, next step is state assignment and construction of a state table. So now I am going to assign the states and construct a state table. Yes, sir. Please observe here. Now I am going to give the state assignment and construct a state table. Okay. So how to assign the states? Please observe how to assign a state. State assignment. Okay, next is we have total A, B, C, D, E, F. Total 5 different states. Yes, sir. So we have total 5 different states. So I am going to assign each of the state. Okay. Now I am going to assign each of the state as a bit. So let me assign each state. So how you can assign the states? Sir, very easy. We can assign a reset state as a 0, 0, 0 state, state B as a 0, 0, 1 state, state C as a 0, 1, 0 state. Sir, is it mandatory to assign the state in this way? No, it is not mandatory. You can assign any. But in order to make the things easier while designing, we will try to keep it in this order only. 0, 1, 1. Yes, sir. 1, 0, 0. Yes, sir. 1, 1, 1, 0, 1. So how many total number of states needed? Sir, total number of states are 5. Total number of states are 5. How many number of flip-flops needed? Sir, for 5 states, number of flip-flops needed will be equals to 3. Yes. So number of states needed will be equals to 3. Yes, sir. Now please observe here. I am going to construct a state table now. I am going to construct a state table now. This is your state table. So in a state table, first of all, we need to write present state. Yes, sir. Then write next state, next state, next state with x is equals to 0 and x is equals to 1. Is it okay? Yes, sir. Oblique output. So that will give you the information of same. That will give you the information of redundant state. If it exists, then we have to remove. Okay? Yes, sir. So I am representing a modified state table first. Yes, sir. Great, sir. Now please observe here. Present state. This will be your next state, comma, output. So present state is A, B, C, D, E, F. These are your present states. Okay? Yes, sir. So with the present state A, x is equals to 0. What is your next state? For that we need to check the state diagram. Present state A, x is equals to 0. Next state is A only, sir. Output is 0 only, sir. Great. So output is 0 only, sir. Great. Again, present state A, x is equals to 1. Next state B, output 0 only, sir. Very good. Present state B, x is equals to 0. Present state B, x is equals to 0. X is equals to 0. Next state C, output 0, sir. Present state B, x is equals to 1. Next state B, output 0, sir. Very good. Come to the C state. Present state C, x is equals to 0. Next state D, output 0. Present state C, x is equals to 1. Next state B, output 0, sir. So B 0. Present state D, x is equals to 0. Next state E, x is equals to 0. Next state E, output 0. Present state D, x is equals to 1. Next state B, output 0. Next state B, output 0. Present state E, x is equals to 1. Next state F, present state E, x is equals to 0, x is equals to 0. Next state A, output 0. We have A 0. We have A 0. Present state E, x is equals to 1. Next state F, output 0. So F 0. Present state F, x is equals to present state F, x is equals to 0. Next state C, output 0. C 0. Present state F, x is equals to 1. Next state A, output 0. A output 1. Output 1. Is it okay? So this is your modified state table. It helps us to understand whether any redundant state is existing or not. Since we have designed in a proper way, so there is no possibility of a redundant. Redundant is only possible in case if we are not analyzing all of the states. Since we have known about the sequence, so we have designed in the same fashion. So there is no redundant state. We have to go by the 3 flip-flops. Is it okay? Now this table helps us to find the excitation table. Depending upon the present state and next required state, with the present input x, we can find excitation needed onto the flip-flops. So how many flip-flops are needed? For 5 states, how many flip-flops are needed? For 5 states, how many flip-flops are needed? M is less than or equals to 2 to the power n. So n is equals to 5. It means 5 flip-flops are needed. 5 JK flip-flops are needed. Is it okay? In order to construct this, sorry, 3 JK flip-flops are needed. 3 JK flip-flops are needed in order to construct this sequence detector. Great, sir. Now from this table, I am going to fill the excitation table. From this table, I am going to fill the excitation table. Is it okay? Yes, sir. So this excitation table is a little bit bigger. Let me show you. Presently, it is just looking like 0 1 0 1 0 1. But let me change. Let me do it. Let me write it here. So it will be very easy for you. Let me write it here. Okay. Up to this part, everything is clear. If you have any issue with anything, please feel free to ask. If you have any issue with anything, please feel free to ask. Great. Up to this, everything is clear. Great. So we have total 3 flip-flops. So we can say the outputs of the flip-flops as Q0, Q1 and Q2. Okay. So I am taking Q2 as a MSB in order to write the expressions in a easier manner. So Q2, Q2, Q1, Q0 is the outputs of the 3 flip-flops. And the next states of the flip-flops are Q2 plus 1, Q1 plus 1, Q0 plus 1. Okay. Q2 plus 1, Q1 plus 1, Q0 plus 1. I'm hoping up to this part everything is clear. Great, sir. So x may be 0 or maybe 1. There is a 2 possibility for x. X may be 0 or maybe 1. There are 2 possibility for x. Yes, sir. X may be 0 or x may be 1. So we have an input x and Q2, Q1, Q0. Based on input x, Q2, Q1, Q0, how many possibilities? Are total 16 possibility. Total 16 possibility. X may be 0, x may be 0. If x is 0, you can say, sir, x 0, Q2, Q1, Q0, 0, 0. Present state, present input, present state. So present input 0, present state 0, 0, 1. Present input 0, present state 0, 0, 0, 1, 0. Present input 0, present state 0, 1, 1. Present state 0, present input 1, 0, 1. 1, 0, 0. Present state 0, present input 1, 1, 1, 0, 1. Present state 1. Why, sir? Because how many states we have? Only 5 different states we have. So all the 5 states already I have taken. 0, 1, 2, 3, 4, 5. Is it okay? Yes, sir. So up to this, we have present state 0 and all the possibilities of Q2, Q1, Q0. Rest of the possibilities of Q2, Q1, Q0 is all are 0, sir. So we need not to take care, because they does not exist. Only the states available are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. What about other state 1, 1, 1? It will not exist. Okay, so for that, input to the j and k will be, you can say, don't care. Why? Because the state is not existing. Yes, sir. Great. So now with x is equals to high, again, there is a possibility x is equals to high and state is 0, 0, 0. X is equals to high and state is 0, 0, 1. State x is equals to high and 0, 0, 0, 1, 0. X is equals to high and 0, 1, 1. X is equals to high and the present state is 0, 1, 0, 0. X is equals to high and the present state is 1, 0, 1. Is it okay? Yes, sir. So now we have all the possibilities of the present state and a present input. Is it okay? Yes, sir. Depending upon that, we need to write a next state. So what is the present state, sir? Present state is state A. Your present state, sir, your present state is state A. Your present state is state A, sir. So for state A, if x is equals to 0, sir, what will be the next state? If x is equals to 0, sir, what will be the next state? 0, sir. Output 0, sir. Next state 0, sir. Output 0, sir. So next state is A, that is 0, 0, 0, and output is 0, sir. Great, sir. Again observe. If the present state is B, with x is equals to 0, what is next state? C. If the present state is B, what is the state B? Sir, state B is 0, 1, 0, 0, 1, sir. With x is equals to 0, present state 0, 0, 1. Next state, sir, C. What is C state? 0, 1, 0. So what you will get here? 0, 1, 0. Is it okay? And what is the output? Sir, output is a 0. Output will be high only when all the input sequences got detected. Is it okay? Yes, sir. Again observe here. Present state C, x is equals to 0. Next state D, output 0. Next state D, output 0. Present state is a C. Present state is a C. Present state is a C. X is equals to 0. Next state is D. Next state is D. What is D, sir? D is 0, 1, 1. What is D, sir? 0, 1, 1. So we will get 0, 1, 1. What about the output, sir? 0, 1, 1, and output is a 0. So we are getting 0. Great, sir. It's very easy. Present state D. X is equals to 0. What is the next state, sir? Present state D. X is equals to 0. What is the next state, sir? E. Output 0. E, output 0. So what is E, sir? E is 1, 0, 0. So we are getting 1, 0, 0. And what about the output, sir? Output is 0, sir. So you will get output here 0, sir. Is it okay? Great, sir. Again observe. Present state 1, 0, 0. Present state 1, 0, 0. Present input x is equals to 0. 1, 0, 0. X is equals to 0. Please observe. 1, 0, 0. 1, 0, 0 is your state E. X is equals to 0. Next state A, output 0. Next state A, output 0. What is the state A? 0, 0, 0 is the state A. So you will get 0, 0, 0. Output 0. Is it okay? Great, sir. Again observe present state. Present state is 1, 0, 1. X is equals to 0. It means present state is 1, 0, 1 is your state. 1, 0, 1 is your state E. 1, 0, 1 is your state F. 1, 0, 1 is your state F. X is equals to 0. Next state is C. What is C? Sir, 0, 1, 0. Output 0. 0, 1, 0. Output 0. 0, 1, 0. Output 0. Is it okay? Great, sir. Again observe. Next is if present state is A. If present state is A, x is equals to 1. Next state is B, output 0. Next state is B, output 0. So if present state is A, let me write it. If present state is A, present state is A. X is equals to 1. The next state is B. Next state is B. Output 0. What is B? 001. Output 0. So 001. We will get 001. Output 0. Is it okay? Yes, sir. Great. If the present state is 001, it means present state is B. If the present state is B, please observe here. Present state is B. X is equals to 1. Next state is B. 0. B 0. B 0 means sir 0 0 1 0. Again, present state is 0. Present state is 0 1 0. That is state C. Output 1. Present state C. Input X is equals to 1. Present state C. Input X is equals to 1. X is equals to 1. Next state B. Sorry. Next state is B. Output 0. So, sir, next state is B. Output 0. What is B? 001. Output 0. Great, sir. 011. Present state is sir 011. 011 is your D state. Present state is D. X is equals to 1. Next state B. Output 0. B output 0. B is 001. Output 0. Present state is 100. X is equals to 1. 100. X is equals to 1. State E. Present state is E. X is equals to 1. How to remove this? Present state is E. X is equals to 1. Present state is E. X is equals to 1. Next state is F. Output 0. F means 101. So, next state is F. 101. Output 0. Present state F. Present state F. Present state F. X is equals to 1. Present state F. X is equals to 1. Next state A. Output 1. Next state A. Output 1. A means 000 state. Output 1. This is how we have to fill the present state, next state. Is it okay? And output Y. Now, based on the present input and present state, we can write excitation needed onto the JK flip-flop. Yes, sir. So this is 0 0 0 0 is the binary of 0. Please observe, it may or may not be in the sequence. 0 0 0 1 is the binary of 1. 0 0 1 0 is the binary of 2. 0 0 1 1 is the binary of 3. 0 1 0 0 is the binary of 4. 0 1 0 is the binary of 5. 1 0 0 is the binary of 8. What about 6 and 7? 6 and 7 are don't care condition. Then this is the binary of 9. This is the binary of 10. This is the binary of 11. This is the binary of 12. This is the binary of 13. What about 14 and 15? Sir, they are also don't. Is it okay? Yes, sir. Now, depending upon the present state Q and next state Q1, Q2 plus 1, we can write excitation needed over the J and K flip-flop. Yes, sir. So now please observe here. Please observe the present state Q2. So what is Q2 and Q2 plus 1? Observe Q2 and Q2 plus 1. Observe Q2 and Q2 plus 1. For 0 0. For 0 0, JK flip-flop excitation table. For 0 0, sir, 0 don't care. So 0 don't care. Sorry, 0 don't care. Is it okay? K2, K2? Yes, sir. Now again observe. Observe Q2 and Q2 plus 1. 0 0. 0 0 means, sir, 0 don't care. Great, sir. From the excitation table, I am writing here 0, 0, 0, don't care, sir. 0, don't care, sir. Again, observe for 0, 1. For a 0, 1, what we will get in the excitation table of JK flip flop? For a 0, 1. Sir, for a 0, 0, we will get a 0, don't care. For a 0, 1, we will get 1, don't care. So, for a 0, 1, we will get 1, don't care. Yes, great, sir. Again, observe for 0, 1, 0. For 1, 0, we will get don't care 1. Yes, sir. Again, observe for 1, 0. Don't care 1, sir. For 0, for 0, 0. Don't care 1, sir. For 0, 0. Don't care 0, don't care, sir. Okay, 0, don't care. For 0, 0, we will get 0, don't care. Yes. For 0, 0, 0, don't care. For 0, 0, 0, don't care. For 0, 0, 0, don't care. Again, observe for 0, 0. For 0, 0. For 0, 0, 0, don't care, sir. Again, observe for 0, 0. 0, don't care, sir. Again, observe for 0, 1, 1. For 1, 1. For 1, 1, we get, sir, don't care 0. And for 1, 1. Sorry, for 1, 0. For 1, 0. For 1, 0. For 1, 0, we will get for 1, 0. For 1, 0, we will get 0. Don't care 1. Is it okay? Yes, sir. Similarly, you need to observe for writing the excitation. From the excitation table, you need to observe Q1 and Q1 plus 1. Based upon Q1 and Q1 plus 1, you can write excitation needed over J1 and K1. Is it okay? Yes, sir. Similarly, you can observe excitation over Q0 and Q0 plus 1. Based upon Q0 and Q0 plus 1, you can find excitation needed over J0 and K0. Is it okay? So this is how we have to fill this table. Is it okay? Great, sir. Now we have J2, J1, J0, K2, K1, K0. We need to find the minimized expression in order to implement the logic circuit. I'm hoping up to this part everything is clear. Great, sir. Now please observe. I'm going to write the minimized expression now. I'm going to write the minimized expression now. Okay? Yes, sir. First observe J2. First observe J2, K2. So J2 and K2. First observe J2, K2. Okay? Yes, sir. So please observe J2 onto the binary condition of 0, 1, 2. 0, 1, 2. Don't care 0, 1, 2. 0, 1, 2. So let me write it here in terms of X. In terms of X, Q2, Q1, Q0. We have X as a MSB. So X Q2 bar, X bar Q2, X Q2, X Q2 bar. X Q2 bar. So bar not needed. Yes, sir. Further we have Q1 bar, Q0 bar, Q1 bar, Q0, Q1, Q0, Q1, Q0 bar. X bar, Q2 bar, X bar, Q2, 𝑥𝐿2 and 𝑥𝐿2 bar. Q1 bar, Q0 bar, Q1 bar, Q0, Q1 Q0 and Q1 Q0 complement. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Further, if you observe here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Now please observe here. Now please observe here. We are getting 0, 0, 0. Let me copy that part. So we need not to design it again and again. 1, 2. Okay. Now please observe here. About J2. 0, 1, 2. 0, 1, 2 are filled by 0. 0, 1, 2 are filled by 0. Yes, sir. Then 3, 4, 5. 3, 4, 5. 3, 4, 5 are with the don't care. 4 and 5 are with the don't care. Then 6 and 7 are missing. So 6 and 7 are also treated as a don't care. 6 and 7 are also treated as a don't care. Come to 8. 8, 9, 10, 11. 8, 9, 10, 11 are filled by 0. 8, 9, 10, 11 are filled by 0. Then 13, 14, 12, 13. 12 and 13 are don't care. And what about these two? These two are also taken as don't care. Is there any chord possible? No, sir. Is there any pair possible? Yes, sir. There is a pair possible, and this is the possible pair. There is only one in J2. Is it okay? Yes, sir. So we are getting X bar Q1 Q0 as J2. Is it okay? Great, sir. What about K2? I'm going to write directly. What about K2, sir? Don't care, don't care, don't care, don't care. So 0, 1, 2, 3. Don't care. 0, 1, 2, 3 are don't care. Yes, sir. Then 4, 5, 8. 4, 5 are 1. 8 is again don't care. 9, 10, 11 don't care. 9, 10, 11 don't care. Then 9, 10, 11, 12, 0, 13, 1. 12, 0, 13, 1. Is there any chord possible or octet possible? Sir, 6 and 7 are don't care. Yes. What about 14, 15? They are also don't care. So best is to take a chord here. This chord and this chord. Is it okay? Yes, sir. So what is the minimized expression for K2? We have minimized expression for K2 as X bar plus of Q0. Is it okay? Yes, sir. There is only 1 0 the entire K2. Great, sir. Hoping you are able to understand up to this part. Great, sir. So in the same fashion, we can write for J1 also, J0 also, K1 also, and K0 also. Is it okay? Yes, sir. So I'm just going to fill it out for J1, K1, and J0, K0. For J1, K1. So if you observe for J1, what is J1? J1 is 0, then 1, don't care, don't care. 0, 1, don't care, don't care. 0, 1, don't care, don't care. 0 1 don't care, don't care. 0 don't care, 1 don't care. 0 don't care, 1 don't care, because 6 and 7 all already don't care. Yes sir. Then if you observe here, 0, okay, I made a mistake somewhere. Again 0 1 don't care, don't care. Okay, 0 1 0 0, 0 1 0 0. Up to this part, okay. 0 1 don't care, don't care. 0 1 don't care, don't care. Then 0 onto the binary condition of 0 1 double 0, 0 1 0 1 double 0. Yes. Then 0 1 double 0. Then don't care, don't care, double 0. Don't care, don't care, double 0. These four are don't care only. These four are don't care only. Yes sir. So how to find the minimized expression for this one? So it's very easy. You can take one chord. With this chord we are getting x bar naught. This is your J1. Great. What about J K1 sir? K1 is don't care 0 1. So don't care 0 1. Okay. Then don't care, 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 don't care. Then again double 1 don't care, don't care, double 1 don't care, don't care. So is there any octet possible? Yes sir. We can have one chord here, octet here. This octet is possible sir. Again this octet is possible. With a 2 octet we are getting x plus of q naught as k1. Is it okay? Similarly you can find for j0 and j1 also. Similarly you can find for j0 and j1 also. Let me write it for you. j0 and k0 also. So we need to find here again j0 k0. So j0 is, we have to observe the first four digits. Okay. So 0 don't care, 1 don't care, 0 don't care, 1 don't care, 0 don't care, 1 don't care. Yes sir. Then 0 don't care, 1 don't care. Then observe this 0 don't care, 1 don't care, 0 don't care, 1 don't care, 0 don't care, 1 don't care. These four are cross only. Now 1 don't care, 1 don't care, 1 don't care, 1 don't care. Is there any pair or octet possible? Yes sir. A chord is possible, this one. Octet is possible, these two octets are possible. So J0 we are getting x plus of 1. J0 we are getting x plus of. Is it okay? Great sir. J0, for J0 we are getting x plus of q1. Hoping up to this part everything is clear. There is no issue, nothing. Great. Now again observe here K0. For K0 you can say sir, for K0 again observe don't care 1 don't care 1 don't care 1 don't care 1. Okay. Then don't care 1 don't care 0 don't care 1, don't care 0. These 4 are don't care only. Last 4 are don't care 0, don't care 1. Don't care 0, don't care 1. So how many loops or chords are possible? Octates are possible, sir. There are 2 octates are possible. You can take this as an octate as well as this as an octate. So the output J0 will become K0 will become Q2 plus of X bar plus of Q. Is it okay? Yes, sir. So now we have all the expressions. Now only we need to implement the logic circuit. Now we have all the expressions, only we need to implement the logic circuit. Hoping now you have obtained this to be very easy. Next is your circuit implementation. So how to implement a circuit? We have J2. What is the value of J2? Please observe here. J2 is X bar Q1 Q0. X bar Q1 Q0. X bar Q1 Q0. So I have connected X bar Q1 Q0. Is it okay? J2 is equals to X bar Q1 Q0. Yes, sir. Let me show you. Please observe here. X bar Q1 Q0 is your J2. Yes, sir. What about K2? K2 is X bar Q0. X bar plus Q0. So X bar plus Q0. For representing bar, we can show this bubble. Is it okay? Yes, sir. So X bar Q0. Now come to the X bar plus Q0. Is it okay? Come to the J1 X bar Q0 AND gate X bar Q0. Yes, sir. X bar Q0. What about next part K0? K0 is X plus Q0. So OR gate is needed. X plus Q. Is it okay? Yes, sir. Similarly, observe the last J0 K0. So J0 is X plus Q1. So I'm representing X plus Q1. And what about K0? K0 is representing Q2 plus X bar. So this will be your Q2 plus X bar. So this is our desired function. What about output? Output is also the function of X. Yes, sir. So what about the output Y? We need to write the expression for output Y also. Output Y. If you observe output Y, then output Y is represented here. Output Y is represented here. Yes, sir. So we need to find the minimized expression for output Y also. What about the output Y? It is only going to be high onto the binary condition of 13. At all other conditions it is 0. Only onto the binary condition of 13. Okay. Yes, sir. So let me show you about the output Y also. Output Y also. Okay. So for output Y, we need to represent a K-map. Let me copy this. Okay. Now please observe, we also have to find the output Y. So I am interested to find the output Y also. Please observe here. Let me show you output Y also. Okay. Yes, sir. Please see output Y. Only onto the binary condition of 13 it is high. Yes, sir. So why we have x bar q2 bar, x bar q2, x q2 and x q2 bar, q1 bar q0 bar, q1 bar q0, q1 q0, q1 q0 complement. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So everywhere it is 0. Yes, sir. Everywhere it is 0 except onto the binary condition of 13. What about 14, 15 and 6 and 7? They are don't care. So we have one pair possible here. With this pair you are getting y is equals to x q2 into q0. So x q2 into q0. Please observe here. This is q0. This is q2 x q2 into q0. Only onto the binary condition of 13 it is high. Yes, sir. Only onto the binary condition of 13 it is high. Yes, sir. So x q2 and q0, x q2 q0, x q2 q0. Wrong. X q2 q0. Yes, sir. This is x q2 not your output y. So this is our desired sequence detector. Basically now we have designed our desired sequence detector. So this sequence detector is going to identify the sequence that is 1, the sequence that is 1 0 0 0 1 1. So if you want to design a sequence detector to detect a sequence 1 0 0 0 1 1, then it can be designed in this manner. So why you have taken all these things? So that you will be able to understand. Now you know what are the purpose of different state diagram, how a sequence detector can be designed, what is a state table, and how we can construct a state excitation table from the state table. Is it okay? So this is all about the sequential circuit. I have completed the entire sequential circuit, including this class. This class is very important. If you have missed any part of the entire class, you must go through that, because this class is very important. Hoping up to this part you have enjoyed a lot. Great. So thank you everyone. Thank you everyone.